Hello there and welcome to the Sleepy Narrator. I'm so happy you're joining me. Tonight, we're going to drift softly through the skies above, uncovering the hidden workings of weather. Those calming breezes, booming thunderheads, delicate snowfalls, and sun-warmed afternoons that shape the ever-changing mood of the heavens. Think of this as your invitation to float weightlessly among the clouds while staying tucked up cozy wherever you are. A small word of caution before we begin. While this video is crafted to help you relax and ease into rest, there's always the slight chance it could be fascinating enough to keep your attention a bit longer. But if you do find yourself wide awake at 2 in the morning thinking about towering cumulonimbus clouds or the spinning Coriolis effect, well, at least you'll come away with a touch more knowledge. Before we truly begin, I'd love to know, where in the world are you watching from, and what time is it right now? Whether it's midnight, dawn, or somewhere in between, it's wonderful to share this moment with you. If you enjoy calming journeys of curiosity like this, please consider liking this video and subscribing to the channel. It helps the Sleepy Narrator grow and allows more people like you to drift off with a head full of gentle wonder. And just a small reminder, while we'll discuss temperature, pressure, and a few ways your body might react to weather, this video is purely for education and relaxation. It isn't medical advice or a replacement for professional care. If you have health concerns, especially related to heat or cold, please reach out to a qualified medical professional. So, close your eyes if you'd like, let your shoulders relax, and take in a deep, slow breath. Tonight, we're going to explore how weather truly works, the science behind each raindrop, rainbow, and distant rumble in the sky. Let's begin with something that surrounds us constantly, yet often goes unnoticed unless it misbehaves: the air itself. We live at the bottom of a vast, invisible ocean of gases, a gently swaying sea called the atmosphere. Unlike the ocean of water, we don't need snorkels or tanks to breathe here, though it can sometimes make your hair misbehave or send your papers flying off the table. The atmosphere is the stage on which all weather unfolds. Proportionally, compared to the Earth, it's about as thin as the skin on an apple. Most of it clings closely to the planet in a narrow band. If you've flown in an airplane and looked out the window while cruising at 35,000 feet, you've already risen above a significant portion of it. The atmosphere is layered, with each stratum having its own personality, like the layers of a cake, though far less edible. The lowest layer, where all the weather we experience actually occurs, is called the troposphere. It's where clouds gather, rain falls, and winds cause mischief. On average, the troposphere stretches about 7 miles high, though it rises taller near the equator and becomes shallower closer to the poles. Above it lies the stratosphere, home to the ozone layer, Earth's very own pair of sunglasses that protect us from the sun's harsher rays. Higher still is the mesosphere, where meteors streak and burn across the sky. Beyond that lies the thermosphere, a realm where auroras shimmer and satellites orbit, with temperatures soaring to thousands of degrees Fahrenheit, though it wouldn't feel hot, as the air is too thin to transfer heat. And at the very fringe, merging softly with space, is the exosphere. This whisper-thin edge contains only scattered molecules that eventually drift away into the cosmos. But for now, let's stay snug within our home layer, the troposphere. Here, the air is mostly nitrogen, making up about 78% of the mix. Oxygen follows at around 21%. The remainder is a delicate cocktail of trace gases: argon, carbon dioxide, and varying amounts of water vapor depending on your location. Not the most glamorous recipe, but one perfectly suited for life. Now, how does air behave? This is where the story of weather truly begins. Air is a fluid just like water. It flows, swirls, tumbles, and most importantly, it reacts to changes in temperature and pressure. Warm air rises because it is less dense, while cold air sinks since it is heavier. This simple rule, warm air up, cold air down, is the beating heart of weather. When the sun shines on Earth, it doesn't heat everything evenly. The equator receives abundant sunlight while the poles get little. Land heats faster than water, and mountains are colder than valleys. These uneven patterns create pockets of warm and cool air. And since nature adores balance, the atmosphere constantly attempts to even things out. Imagine a sunny patch of land. The sun warms it, and the air above begins to rise. As it climbs, it cools. Cooler air cannot hold as much moisture, so if water vapor is present, it condenses into tiny droplets, forming clouds. Meanwhile, the surrounding cooler air rushes in to replace the rising pocket. This movement is called convection, the same principle that circulates bubbles in a boiling pot of soup, just on a far greater scale. Air also carries weight. Not much, but enough that all the layers stacked above you add up to around 14 pounds of pressure per square inch at sea level. Imagine a gentle cat pressing down on every inch of your body all at once. That's atmospheric pressure. It varies with altitude and with weather. High-pressure systems are like the quiet moods of weather, calm, stable, and often associated with clear skies. Air slowly sinks, discouraging cloud formation. Low-pressure systems, however, are restless. Rising air encourages cloud growth and often leads to rain or storms. The difference in pressure between regions drives winds, as air flows from areas of higher pressure toward lower pressure, trying to restore equilibrium. Now add the Earth's spin into the mix. Our planet spins rapidly, over 1,000 miles per hour at the equator. This rotation twists moving air, an effect known as the Coriolis effect. In the northern hemisphere, winds are deflected to the right, in the southern hemisphere to the left. What may sound like magic is simply physics in action. Moisture, topography, and even the time of day all play their part, creating constant motion. The atmosphere is endlessly shifting, never the same from moment to moment. Even on a still day, tiny invisible currents, subtle humidity changes, and hidden temperature gradients dance around us. What's truly elegant is that this entire swirling system runs without a conductor, without a switch. It is self-organizing, driven by physics, gravity, and the golden principle of thermodynamics, energy spreads. Heat flows from hot areas to cold, pressure seeks balance, and water evaporates, falls, and rises again. The atmosphere continually strives for equilibrium. It never fully achieves it, but it never stops trying. And that, in essence, is why we have weather. Because Earth is a restless sphere wrapped in warm gases, spinning and shining beneath the sun. Every gust, every cloud, each drop of rain is part of this ongoing dance toward balance. So the next time you notice the breeze in your hair or clouds racing overhead, you'll know you're watching a fragment of an ancient, invisible ballet choreographed by sunlight and stirred by gravity. And it all begins in the air we breathe. Now let's talk about the ultimate puppeteer of weather, the sun. Though it rests some 93 million miles away, it orchestrates every gust, storm, and drizzle here on Earth. Without it, our planet would be a frozen, lifeless rock. No winds, no clouds, no forecasts of scattered showers ruining our socks. The sun's energy drives everything. It arrives as sunlight, electromagnetic radiation, warming the Earth's surface. But here's a twist. The sun doesn't heat the atmosphere directly. Instead, it warms the land, oceans, and surfaces, which then radiate heat back upward. Like a stovetop warming the air above it after being switched on, Earth itself heats the air. Not all areas absorb sunlight equally. Because of Earth's spherical shape and its tilt, some regions bask in direct sunlight, while others make do with a weaker glow. The equator receives sunlight more directly, while the poles are left with only glancing rays. This imbalance fuels constant motion. Near the equator, warm air rises, creating a region of lower pressure at the surface. Cooler, higher pressure air rushes in to fill the gap. Meanwhile, the rising air drifts poleward and cools as it goes, eventually sinking at higher latitudes before returning toward the equator along the surface. This great circulation forms convection cells. There are 3 primary cells in each hemisphere: Closest to the equator lies the Hadley cell. Above that, in the mid-latitudes, is the Ferrel cell, and near the poles sits the polar cell. Together, these circulate heat from equator to pole, acting like vast invisible conveyor belts. Within these cells, recognizable wind systems emerge. Near the equator, steady trade winds blow from east to west, vital currents that sailors relied upon for centuries. In the mid-latitudes, we encounter the westerlies, winds blowing west to east, which carry weather systems across continents. Near the poles, polar easterlies sweep cold air from east to west. But remember, none of these travel in straight lines. Thanks again to the Coriolis effect, winds bend and curve instead of racing directly. This is why cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern. High above, narrow bands of swift-moving air, jet streams, snake across the sky. These flow at the boundaries between major air masses, reaching speeds over 200 miles per hour. The polar jet stream is the most famous, marking the divide between frigid polar air and warmer mid-latitude air. Like rivers of wind, jet streams guide storms, steer weather, and even shorten flights traveling eastward. And because Earth is tilted on its axis, about 23.5 degrees, we have seasons. As Earth journeys around the sun, different regions tilt toward or away, receiving more or less sunlight. The result is summer and winter, with spring and autumn balancing in between. This shifting sunlight reshapes temperature patterns, adjusts wind, influences storms, and stirs oceans. Speaking of oceans, those vast blue basins covering over 70% of Earth are anything but passive. They store heat like giant batteries, releasing it slowly. Land heats and cools quickly, water does not. This is why coastal climates are gentler than inland ones. Ocean currents, like great conveyor belts of water, redistribute heat too. Warm currents transport tropical warmth across oceans, moderating climates thousands of miles away. And when global ocean patterns shift, as with El Niño or La Niña events, their influence ripples across the entire planet, shaping rainfall, drought, and temperatures. So, without leaving your comfortable spot, you've now drifted through the great choreography of Earth's weather system. The sun unevenly warms our planet. That warmth makes air rise and fall. Spinning Earth deflects winds into graceful curves. Jet streams guide them across the sky, while the planet's tilt ensures variety across the seasons. The result is a world where no 2 days are ever alike, where every breeze and every raindrop is part of a vast ballet powered by sunlight and motion. Moisture in the air is one of those invisible companions you rarely think about until it makes its presence known, whether by frizzing up your hair or fogging your glasses on a damp morning. Yet this hidden water vapor is central to weather everywhere. It builds clouds, brings rain and snow, powers storms, and paints some of the most breathtaking sights in the sky. In short, moisture is the atmosphere's secret ingredient. Even when skies look perfectly clear, it's still there, drifting unseen. Let's begin with humidity, the technical term for water vapor in the air. Water vapor is simply water in its gas phase, and the air can hold more or less of it depending on its temperature. Warm air can hold a greater amount, while colder air can hold less. This is why summer days often feel sticky and heavy, while winter days feel crisp and dry. It's not just a trick of the senses. There's literally more moisture floating around in the heat than in the chill. Meteorologists measure humidity in 2 primary ways: absolute humidity and relative humidity. Absolute humidity is the straightforward measure of how much water vapor is present in the air. Like saying there are 12 grams of water per cubic meter. Relative humidity, however, is more about context. It tells us how much water vapor is in the air compared to how much it could hold at that temperature. So, if the relative humidity hits 100%, the air is completely saturated and can't hold any more. At that point, condensation occurs and you'll see dew, fog, or clouds forming. You've likely felt the effects yourself. On a hot summer afternoon, high humidity makes everything feel heavy and slow. That's because your sweat doesn't evaporate easily in damp air, and sweating is your body's natural cooling system. In contrast, dry air allows sweat to evaporate quickly, cooling you down but sometimes leaving your skin feeling parched. Now let's shift our attention to clouds, the sky's ever-changing artwork. Clouds may look airy and feather-light, but each one is made up of countless tiny water droplets or ice crystals, depending on the temperature. These droplets are so minuscule that it takes about 1 million of them to create a single raindrop. And though they seem delicate, an average cumulus cloud, the fluffy white ones we often draw as children, can weigh hundreds of thousands of pounds. Imagine something as heavy as a jumbo jet floating above you, supported by nothing more than air currents. But how do these sky sculptures form? It all begins with evaporation. Water from oceans, lakes, rivers, and even damp soil warms under the sun, turning into vapor and rising. Warm air is buoyant, so the vapor ascends. As it rises higher into the atmosphere, the air pressure drops, causing the air to expand and cool. Cooler air holds less water vapor, so the excess condenses into tiny droplets or ice crystals. These cling to microscopic particles like dust, pollen, or salt, called cloud condensation nuclei. These invisible specks serve as seeds around which clouds grow. Different types of clouds emerge depending on how air rises and how much moisture it carries. If the air rises gently, you get stratus clouds, flat, gray sheets that often blanket the sky in overcast gloom. If the air rises more quickly, it forms cumulus clouds, those familiar cottony puffs drifting lazily across summer skies. And if conditions are especially moist and unstable, cumulus clouds can grow taller and taller, transforming into massive cumulonimbus towers, the giants responsible for thunderstorms. Other clouds tell their own stories. Cirrus clouds, delicate wisps high above, are made mostly of ice crystals. They resemble feathers and can signal changes in the weather. Lenticular clouds, often mistaken for UFOs, form over mountains in smooth, disc-like shapes. Mammatus clouds hang down like pouches, often appearing during turbulent weather. There's even altocumulus castellanus, a formation that looks like rows of little turrets marching across the sky. The names may sound magical, but each belongs to the science of atmospheric observation. Yet, forming a cloud doesn't mean rain will follow. Droplets must grow large enough to overcome air resistance before falling to the ground. This growth happens through coalescence, where droplets collide and merge. Once they reach roughly 2 millimeters across, gravity pulls them down as raindrops. In colder clouds, ice crystals may form instead, attracting moisture until they're heavy enough to fall as snow. Here's an interesting fact. Raindrops don't actually look like teardrops, despite cartoons suggesting otherwise. Instead, they resemble tiny hamburger buns, rounded on top, flattened on the bottom by air resistance. If a drop grows too large, it may split apart mid-fall into smaller droplets. And not all precipitation falls as liquid. When the air remains below freezing all the way from the cloud to the surface, snow forms. Snowflakes are crystals of ice, their shapes depending on temperature and humidity. Some are slender needles, others flat plates, and the classic six-armed star shape only occurs under certain precise conditions. It's true that no two snowflakes are exactly identical, but with quintillions of flakes falling each winter, many are nearly indistinguishable. Sometimes, precipitation takes on more complex forms. If snowflakes partially melt while descending through a warm layer of air, but then refreeze before hitting the ground, you get sleet, tiny ice pellets that bounce when they land. Freezing rain is trickier. It falls as liquid, but the ground is below freezing, so it instantly coats surfaces with ice, creating dangerous glassy layers. Then there's hail, formed in powerful thunderstorms. A small ice pellet gets lifted by updrafts inside the storm, gaining layer after layer of frozen water each time it rises and falls, until it grows heavy enough to drop. Hailstones can be as small as peas or, in rare cases, as large as grapefruits. But moisture doesn't always need to fall from the sky to make itself known. Sometimes it settles gently, creating dew on cool mornings. Dew forms when the ground cools overnight, chilling the air just above it, and moisture condenses on grass, leaves, or windows. If the temperature drops below freezing, dew transforms into frost, painting intricate ice patterns across the landscape. All of these processes, evaporation, condensation, and precipitation, are part of the water cycle, nature's endless recycling system. Water evaporates from oceans and lakes, drifts upward, forms clouds, rains, or snows back down, and eventually returns to rivers and seas to begin the journey again. This cycle has been turning for billions of years, essential to every living thing. Now, let's shift to one of the atmosphere's most dramatic displays, thunderstorms. Thunderstorms are nature's fireworks, rattling, flashing, pouring, and sometimes pelting the earth with hail. They may seem wild and chaotic, but at their core, they're born from basic ingredients: air, water, and electricity. It all starts with warm, moist air rising into cooler layers above, creating an updraft. Picture a hot summer afternoon. The sun heats the ground all day, and eventually a pocket of air near the surface warms more than the surrounding air. Because warm air is lighter, it begins to rise. As it climbs, it expands and cools. If it contains enough moisture, it eventually reaches its dew point, the temperature where vapor condenses into droplets. This condensation releases latent heat, giving the air an extra lift, almost like adding rockets to a balloon. The cloud continues to grow taller, from a harmless puffy cumulus to a towering cumulonimbus stretching up to 10 miles high, higher than Mount Everest. Inside, chaos reigns. Updrafts shove warm air higher, while downdrafts drag cooler air and falling rain downward. This push and pull powers the storm. Thunderstorms move through 3 stages: cumulus, mature, and dissipating. In the cumulus stage, the cloud forms quietly. In the mature stage, the storm erupts, rain falls, lightning flashes, thunder booms. Eventually, the downdraft cuts off the warm, rising air, and the storm fades. Lightning, of course, is the star of the show. As ice crystals and droplets collide inside the storm, they build electrical charges. Lighter particles carry positive charges to the top, while heavier particles gather negative charges at the bottom. This separation creates an enormous electrical imbalance, millions of volts between parts of the cloud or between cloud and ground. Eventually, the air breaks down, and electricity discharges in a brilliant flash, lightning. A faint step leader of charged particles zigzags downward invisibly until it nears the ground. The intense electric field prompts a streamer to rise upward, meeting it. When they connect, a current surges, producing the blinding flash we see. The air in that path heats to around 50,000 degrees Fahrenheit in microseconds, hotter than the sun's surface. The rapid expansion creates a shockwave we hear as thunder. Because light travels faster than sound, you always see lightning before you hear thunder. To estimate how far away a strike is, count the seconds between the flash and rumble. Divide by 5 and you get the distance in miles. 10 seconds, for instance, means the strike was about 2 miles away. Lightning comes in many forms: cloud-to-ground strikes, intra-cloud flashes within one cloud, and cloud-to-cloud bolts leaping between systems. More exotic types include ball lightning, mysterious glowing orbs, and sprites or blue jets, strange phenomena that burst upward into the mesosphere. Sprites resemble red jellyfish dancing high above storms. Once dismissed as hallucinations, they're now confirmed as real and extraordinary. Despite its beauty, lightning is incredibly powerful. A single bolt can release over 1 billion joules of energy, enough to power a small town for a brief moment. It can spark wildfires, damage buildings, and endanger lives. That's why the advice is simple: when thunder roars, head indoors. Along with lightning, thunderstorms often bring hail, formed by updrafts tossing ice pellets repeatedly through freezing layers. Each journey adds another layer of ice until the hailstone grows too heavy to stay aloft. Hail can be small and harmless or large enough to cause serious damage. Thunderstorms also unleash strong winds. Downdrafts push air down and outward, creating sudden gusts known as downbursts. These can flatten trees and mimic the damage of tornadoes. Speaking of which, while not every thunderstorm spawns them, some can create tornadoes. The most dangerous storms are supercells, which have a rotating updraft called a mesocyclone. This spin comes from wind shear, when winds at different altitudes blow at varying speeds or directions. If a strong updraft tilts that rotation vertical, the entire storm begins to rotate. Under the right conditions, a funnel cloud may form and stretch downward. If it touches the ground, it becomes a tornado. Not every rotating storm produces one, but when they do, tornadoes are among the most violent weather events on Earth. When the atmosphere truly wants to make itself heard, it unleashes tornadoes and hurricanes, two of the most dramatic spectacles in nature's repertoire. These immense tempests are the headline performers of the sky, swirling with raw energy capable of carving paths across landscapes and reshaping coastlines. They're loud, forceful, sometimes terrifying, yet they follow the same fundamental rules that govern all weather: air, water, pressure, and movement, simply turned up to the highest volume. Let's begin with tornadoes. A tornado is a violently rotating column of air that extends from the base of a thunderstorm down to the ground. Though brief compared to hurricanes, they can be astonishingly intense, holding the record for the strongest surface winds ever measured on Earth. Some tornadoes spin with wind speeds over 300 miles per hour, faster than a Formula One race car, and far less forgiving. The exact process of tornado formation remains an active area of study, but meteorologists have identified key ingredients. The first is a strong thunderstorm, often a supercell. Supercells are unique because of their rotating updraft, called a mesocyclone. This rotation usually begins with wind shear, winds at different altitudes blowing in different directions or at varying speeds. Imagine surface winds moving from the southeast, while stronger winds higher up sweep from the west. This setup creates a rolling effect in the lower atmosphere, a horizontal tube of spinning air. When a thunderstorm develops above this zone, its powerful updraft can tilt the horizontal spin vertically. A spinning column of air now stretches skyward, but for a tornado to form, this rotation must tighten and extend downward into a funnel. If that funnel touches the ground, the storm gives birth to a tornado. Not every mesocyclone produces one. Some storms flirt with tornado formation for hours without success, while others produce a twister suddenly, with little warning. Once formed, tornadoes can travel slowly, only a few miles per hour, or race across the land at speeds over 70. Most tornadoes are small and relatively weak, categorized as EF0 or EF1 on the enhanced Fujita scale. These may break tree branches or knock over signs. Occasionally, however, monsters emerge, EF4 or EF5 tornadoes. These colossal storms flatten entire neighborhoods, uproot houses, and toss vehicles like toys. At the top of the scale, EF5 tornadoes are catastrophic, stripping homes from their foundations and leaving landscapes resembling war zones. Tornadoes occur most frequently in the United States, particularly across a region nicknamed Tornado Alley. This stretch of the Central Plains is uniquely suited for their formation, where warm, moist air from the Gulf meets cold, dry air from Canada and the Rockies under vast open skies. Yet tornadoes are not limited to North America. They've been recorded on every continent except Antarctica. Water spouts, tornadoes over water, are common in warm coastal regions. Even countries not known for extreme weather, like the United Kingdom, experience several tornadoes each year, though usually weaker and shorter-lived. Now, let's shift focus to the tornado's larger, longer-lived relative, the hurricane. Hurricanes, also called cyclones or typhoons depending on the region, are massive rotating storm systems born over warm ocean waters. Unlike the brief, violent nature of tornadoes, hurricanes are sprawling, slow-moving engines of atmospheric energy. They can stretch hundreds of miles wide and last for days or even weeks. For a hurricane to form, specific conditions must be met. Warm ocean water, at least 79 degrees Fahrenheit, must extend to a depth of about 150 feet. This warm water is the storm's fuel. Second, a pre-existing disturbance, such as a cluster of thunderstorms, is necessary to kick things off. Third, low vertical wind shear is required. If winds at different heights vary too strongly, they can tear the developing system apart before it organizes. When these ingredients align, the warm ocean water evaporates, adding moist air to the atmosphere. As this air rises and cools, it condenses into clouds, releasing latent heat. That heat fuels further rising motion, drawing in more moisture. With Earth's rotation contributing the Coriolis effect, the air begins to spiral. A low-pressure center develops, forming a tropical depression. If the system strengthens, it becomes a tropical storm. Once sustained winds reach 74 miles per hour, it officially earns the title of hurricane. A hurricane has several distinct parts. At its heart lies the eye, a calm, clear center where winds are light and skies may even appear blue. Encircling it is the eye wall, a ring of towering thunderstorms containing the storm's most violent winds and heaviest rainfall, the most dangerous region. Spiraling outward are rain bands, long curved bands of showers and storms extending hundreds of miles. Hurricanes are measured on the Saffir-Simpson scale, ranging from Category 1 to Category 5. A Category 1 hurricane, with winds between 74 and 95 miles per hour, can damage roofs, trees, and power lines. At Category 5, with winds exceeding 157 miles per hour, destruction is catastrophic, rendering areas uninhabitable for weeks or months. Yet wind isn't the only danger. Storm surge, the rise of sea level caused by hurricane winds pushing water toward shore, is often the deadliest aspect, especially in low-lying coastal regions. Add to this torrential rainfall, sometimes more than 2 feet in just a few days, and the flooding can extend far inland, triggering landslides and washing away entire communities. Despite their destructive power, hurricanes play a role in Earth's climate system. They help redistribute excess heat from the tropics toward the poles, moving thermal energy away from the equator. In a strange way, they are part of the atmosphere's endless balancing act. Unlike tornadoes, hurricanes are easier to track. Satellites, aircraft, and computer models provide meteorologists with days of warning. This allows communities time to prepare, evacuate, and mitigate the dangers. Still, once a hurricane makes landfall, its sheer size and energy are nearly impossible to control. When it moves over cooler water or land, cut off from its warm fuel source, the storm weakens, its winds slow, and its rains fade. What remains is cleanup and recovery, but meteorologically speaking, the storm has completed its arc, from warm seas to whirling colossus to fading memory. Both tornadoes and hurricanes are expressions of the same principles guiding all weather: heat moving, pressure seeking balance, air and water in motion. They're not anomalies, but natural results of an atmosphere alive and restless. Now let's turn our attention to wind itself, the invisible sculptor of our world. Wind cannot be seen, yet it is constantly reshaping the environment. You can feel it tugging your hair, pushing leaves along the sidewalk, or flipping your umbrella inside out on a rainy day. It's playful and destructive, calming and chaotic, yet at its core, wind is simply air in motion. What drives wind? Differences in atmospheric pressure. Air naturally flows from areas of high pressure toward areas of low pressure. The greater the difference, the stronger the wind. Think of it as nature's way of tidying up pressure imbalances. Imagine the atmosphere as a landscape of invisible hills and valleys. Air rolls downhill from high to low, but because Earth spins, it doesn't travel in straight lines. The Coriolis effect once again bends its path, to the right in the northern hemisphere and to the left in the southern. On a planetary scale, winds follow organized patterns. At the equator, where the sun strikes most directly, warm air rises, creating low-pressure zones. This air spreads poleward high above the surface, sinking again near 30 degrees north and south, forming belts of high pressure. From there, surface winds flow back toward the equator, creating steady easterly trade winds. These were so dependable that sailors of past centuries used them to cross oceans, fueling exploration and discovery. Between 30 and 60 degrees latitude, winds blow the opposite direction, from west to east. These westerlies drive many weather systems across continents. Near the poles, cold air sinks, creating the polar easterlies, which bring frigid blasts toward lower latitudes. Beyond these global belts, winds become more personal and local. Along coastlines, sea breezes form as land heats faster than water during the day. Warm air rises over land, and cooler ocean air flows in to replace it, creating refreshing winds from sea to shore. At night, the pattern reverses, with breezes flowing back toward the sea. In mountainous terrain, winds show their own rhythm. By day, slopes warm and air rises, drawing cooler air upward in anabatic winds. At night, cool, dense air slides back down into valleys as katabatic winds. Some katabatic winds are famous. The Mistral in southern France is a fierce, dry wind racing toward the Mediterranean, shaping regional architecture and climate. In California, the Santa Ana winds blow hot and dry from desert to coast, fanning wildfires. And in the Rockies, the Chinook winds, nicknamed snow eaters, descend warm and dry into the plains, raising temperatures dramatically in minutes. Winds also emerge in sudden bursts. Microbursts, powerful downdrafts during thunderstorms, slam air toward the ground, spreading destruction much like tornadoes. Dust devils, on the other hand, are miniature whirlwinds, spinning harmlessly across hot, dry landscapes, stirring dust in narrow spirals. At the other extreme are large systems like gales and cyclones, tied to low-pressure zones and capable of immense power. Yet even the quietest breeze plays a role in shaping our world. Wind transports moisture, scatters seeds, carries pollen, and slowly wears mountains into sand. It sculpts dunes in deserts and drifts in snowy fields. Humanity has long relied on it for sails, for farming signs, and today for renewable energy through wind turbines. Wind also influences how we feel temperature. On a hot day, a breeze cools by whisking away body heat. On a frigid one, it cuts sharply, stripping away the warm air layer near your skin. This is the wind chill effect. It doesn't lower actual temperature but makes it feel colder, sometimes dangerously so. Though often unpredictable, wind still obeys the laws of physics, moving along pressure gradients, influenced by geography and rotation. Whether as a whisper through leaves or a howl in a winter storm, wind is one of the clearest reminders that the atmosphere is alive, in motion, and filled with quiet strength. Temperature is one of the simplest weather elements to notice, yet also one of the most profound. We feel it every moment, whether through the warmth of the sun on our skin or the chill of a frosty morning. It's more than just a number on a thermometer. Temperature shapes nearly every aspect of the weather we experience, guiding winds, forming clouds, and deciding whether precipitation falls as rain, snow, or something in between. But what exactly is temperature? In scientific terms, temperature is the measure of how fast the molecules in a substance are moving. The faster they vibrate, the warmer it feels. The slower they move, the colder it becomes. In the air around us, these tiny molecules of nitrogen, oxygen, and trace gases are in constant motion, colliding billions of times every second. When sunlight warms the ground and that heat rises upward, the molecules jiggle faster, raising the air's temperature. There are several scales for measuring temperature. The most familiar in daily life are Celsius and Fahrenheit. Celsius sets water's freezing point at 0 and boiling point at 100. Fahrenheit sets freezing at 32 and boiling at 212. Scientists often use Kelvin, which starts at absolute 0, the theoretical point where all molecular motion ceases. On the Kelvin scale, there are no negatives. For weather, temperature is never uniform. It varies across space and time, and those variations drive much of what we call weather. Imagine a map with color shading across the globe. Near the equator, bright oranges and reds mark warm zones where sunlight is most direct. Toward the poles, pale blues and whites reflect frigid conditions where sunlight arrives at an angle. Between them lie constant gradients, shifting with seasons, topography, and air circulation. One important factor is altitude. As you climb higher into the atmosphere, the air becomes thinner and cooler. On average, temperature drops about 3.5 degrees Fahrenheit for every 1,000 feet of elevation. This is why mountaintops are often snow-capped even when valleys below bask in warmth. Seasonal changes add another rhythm. Because Earth is tilted on its axis, different regions lean toward or away from the sun during the year. Summer brings long days and intense heating, while winter shortens daylight and reduces solar input. Spring and autumn mark transitions, when temperatures fluctuate and weather can be unpredictable. Temperature also ties into comfort levels. On hot, humid days, the heat index describes how hot it actually feels to our bodies, factoring in humidity. High humidity slows sweat evaporation, making the air feel hotter than the thermometer shows. In contrast, in winter, wind strips away the thin insulating layer of warm air near our skin. The wind chill index explains how cold it feels when air temperature combines with wind speed. Both heat index and wind chill help explain why a 90-degree day with high humidity feels oppressive, or why a 10-degree day with a sharp breeze feels like negative temperatures. Extreme temperatures bring danger. Heat waves can cause dehydration, heat exhaustion, and stress on power grids. Cold snaps threaten frostbite, frozen pipes, and agricultural losses. Yet life has adapted to thrive across these extremes. Camels endure blistering desert heat, while penguins huddle in Antarctic cold. Humans build clothing, shelters, and technologies to live in nearly every environment. Now consider the interplay between temperature and pressure. Air pressure results from the weight of the air above. At sea level, this amounts to about 14 pounds per square inch. But pressure is not constant. It varies with temperature. Warm air expands and becomes less dense, reducing surface pressure. Cold air contracts, increasing density and raising pressure. These differences create high and low pressure systems, the engines that drive much of our daily weather. High pressure systems, sometimes called anticyclones, feature sinking air. As air sinks, it warms and dries, discouraging cloud formation. The result is fair, calm weather with clear skies. In contrast, low-pressure systems involve rising air. As it rises, it cools, moisture condenses, and clouds develop, often bringing rain or snow. Barometers, instruments that measure air pressure, are crucial tools for forecasting. A sudden drop in pressure often signals an approaching storm. A steady rise indicates improving weather. Sailors, farmers, and pilots have long relied on these subtle cues to anticipate conditions. Pressure patterns don't exist in isolation. They interact on scales large and small. On global scales, semi-permanent high and low pressure systems guide climate zones. The subtropical highs near 30 degrees latitude produce deserts where sinking air dominates. The equatorial low fosters constant rising motion, supporting lush rainforests. On regional scales, migrating low-pressure systems and their associated fronts bring day-to-day weather changes. A cold front occurs when cold, dense air pushes under warmer air, forcing it upward. This often produces dramatic weather, towering clouds, heavy rain, and sometimes storms. A warm front, in contrast, occurs when warm air slides over retreating cold air, bringing gradual, steady rain and milder conditions. Stationary fronts linger when neither air mass can overpower the other, resulting in days of clouds and precipitation. Pressure gradients also determine wind speed. The sharper the difference between high and low pressure over a given distance, the stronger the winds become. This is why storms often bring gusty conditions. The atmosphere is working overtime to balance itself. Temperature and pressure shape precipitation as well. Whether rain falls as liquid, sleet, freezing rain, or snow depends on the layers of warm and cold air it passes through on its way to the ground. Sometimes, the line between rain and snow can shift just a few miles, dividing cities into wet streets on one side and winter wonderlands on the other. Now, let's explore another atmospheric element that links directly with both temperature and pressure: humidity. As mentioned earlier, humidity is the measure of water vapor in the air. It influences comfort, cloud formation, and precipitation. Absolute humidity is the total amount, while relative humidity compares it to the maximum air could hold at that temperature. When air reaches 100% relative humidity, it is fully saturated, and condensation occurs. The relationship between temperature and humidity explains many everyday phenomena. For instance, why does dew form on cool mornings? Overnight, the ground loses heat, cooling the air near its surface. When the air cools to its dew point, the temperature at which it can no longer hold all its vapor, moisture condenses into droplets on grass, leaves, and car windows. Fog is essentially a cloud at ground level, forming when air cools near the surface, or when moist air passes over cooler land or water. Depending on conditions, fog may appear as thick blankets reducing visibility to near zero, or as delicate wisps drifting through valleys. Humidity also fuels storms. Warm, moist air contains immense potential energy. When lifted, its vapor condenses, releasing latent heat. This heat adds buoyancy, allowing air to rise faster and higher, feeding thunderstorms, hurricanes, and other systems. Without moisture, weather would lose much of its drama. Yet humidity doesn't just affect weather. It shapes how we experience climate indoors. Too little moisture dries skin, irritates sinuses, and increases static electricity. Too much encourages mold growth, sticky discomfort, and difficulty cooling off. That's why modern buildings often include humidifiers or dehumidifiers, seeking balance. Stepping back, it's remarkable how interconnected these elements are. Temperature, pressure, and humidity constantly influence one another. They weave together into endless combinations, producing everything from calm, clear skies to turbulent storms. Now let's take a journey into the frozen side of weather: snow, ice, and frost. Snow begins as water vapor in clouds, where temperatures are below freezing. Instead of condensing into droplets, the vapor crystallizes directly into ice. The structure of each snowflake depends on the exact conditions: humidity, temperature, and the path it takes while falling. That's why no two flakes are identical, though many are remarkably similar. The classic six-pointed star shape emerges because of how water molecules bond together, but flakes can also form as needles, plates, or columns. Their symmetry reflects the underlying geometry of ice. When snow falls, it transforms landscapes, softening edges, muffling sounds, and blanketing the world in reflective whiteness. Snow can accumulate quickly, especially in lake-effect regions where cold air passes over warmer water, picking up moisture and releasing it as heavy snowfall downwind. Not all frozen precipitation is gentle. Sleet, freezing rain, and hail bring hazards. Freezing rain, in particular, creates coatings of ice on roads, trees, and power lines, leading to treacherous conditions. Hail, born in powerful thunderstorms, can grow into stones large enough to dent vehicles and destroy crops. Frost is another form of frozen weather. It occurs when surfaces cool below freezing and moisture in the air deposits directly as ice crystals. Frost patterns on windows can resemble ferns, feathers, or intricate lacework, natural artistry painted by cold air. Glaciers represent frozen precipitation on a grand scale. Over centuries, layer upon layer of snow compacts into ice, forming rivers of frozen mass that slowly creep downhill. Glaciers sculpt valleys, carve mountains, and serve as vast reservoirs of fresh water. The frozen world interacts with the rest of the climate system. Snow and ice reflect sunlight, a property known as albedo, helping regulate Earth's temperature. When snow cover melts, darker land or water beneath absorbs more heat, influencing seasonal warming. In extreme regions like Antarctica or the Arctic, ice dominates landscapes, shaping ecosystems and weather patterns alike. Yet even in temperate zones, winter brings its icy touch, reminding us of the delicate balance between warmth and cold that defines our planet. Rainbows are among the most enchanting sights in the sky, so simple in appearance yet deeply rooted in the physics of light and water. They remind us that beauty often arises from basic natural principles, sunlight meeting raindrops. While children see magic and myth in their arcs, scientists understand them as evidence of how light bends, reflects, and disperses when passing through water. Let's explore what really happens. When sunlight enters a raindrop, it slows and bends, a process called refraction. Inside the droplet, the light reflects off the inner surface, then exits, bending once more. During this journey, the light splits into its constituent colors because each wavelength bends at a slightly different angle. Red bends the least, violet the most. The result is a spectrum spread into a circle of color, which we perceive as a rainbow. Though we often describe rainbows as arcs, they are actually full circles. From the ground, the horizon blocks the bottom half, so we only see the curved top. From an airplane or mountaintop with the right conditions, observers can sometimes glimpse a complete circular rainbow. The rainbow's order of colors is consistent: red on the outer edge, followed by orange, yellow, green, blue, indigo, and violet. This sequence reflects the gradual change in wavelength across the spectrum. Occasionally, a brighter primary rainbow is accompanied by a fainter secondary rainbow, formed when light reflects twice inside raindrops. In these secondary arcs, the colors are reversed: red inside, violet outside. Rainbows require precise conditions. The sun must be behind the observer, with raindrops or mist ahead. This is why they often appear after showers when sunlight breaks through scattered clouds. Waterfalls, fountains, or even a garden hose can also produce miniature rainbows if the light and angle align. Beyond primary and secondary arcs, there are rarer forms. Supernumerary rainbows appear as faint pastel bands just inside the main rainbow, caused by interference patterns in light waves. Moonbows, or lunar rainbows, occur at night when moonlight, though much weaker than sunlight, refracts through moisture. These often appear white to the naked eye, as human night vision struggles with color, though cameras can capture their faint hues. For centuries, rainbows inspired myths. In Norse tradition, Bifrost was the rainbow bridge linking Earth to the realm of the gods. In Irish folklore, leprechauns supposedly hid pots of gold at their ends. While such tales are fanciful, they reflect humanity's awe at this intersection of weather and light. Speaking of light, let's move to another atmospheric wonder: halos. Halos are circles or arcs of light that form around the sun or moon when ice crystals in high clouds bend incoming light. Unlike raindrops, which produce rainbows through refraction and reflection, ice crystals create halos primarily through refraction alone. The most common is the 22-degree halo, appearing as a ring of light encircling the sun or moon at about the span of an outstretched hand. These halos occur when thin cirrostratus clouds drift overhead. Their ice crystals act like tiny prisms, bending light at predictable angles. Sometimes halos brighten into sun dogs, brilliant spots of color flanking the sun, often appearing like twin fragments of rainbow on either side. In cold climates, sun dogs can be dazzling, painting skies with vivid displays as the sun rises or sets. Other halo effects include light pillars, vertical beams that stretch upward or downward from the sun, or artificial lights. These occur when flat ice crystals reflect light in parallel paths. Circumzenithal arcs, resembling upside-down rainbows high above, appear when light refracts through horizontally oriented crystals. Collectively, these displays remind us that the sky is a natural canvas where ice, water, and sunlight constantly collaborate. Next, let's talk about fogbows and glories. A fogbow is similar to a rainbow but forms in fog rather than rain. Because fog droplets are much smaller than raindrops, they scatter light differently, producing a bow that appears pale or even white, lacking distinct colors. Sailors sometimes called them white rainbows, often spotting them at sea when sunlight filtered through mist. Glories are smaller, colorful rings that encircle the shadow of an observer's head, usually seen when flying in an airplane or standing atop a mountain with the sun behind. They appear when light diffracts around droplets, creating concentric halos of red, blue, and violet. Seeing a glory can feel strangely personal, almost like the sky painting a halo around you. Light phenomena don't stop there. Mirages are another optical trick, born not from water droplets or ice crystals but from layers of air at different temperatures. When light passes through air of varying density, it bends. On hot roads, this bending creates shimmering illusions of water, pools that vanish as you approach. In polar regions, mirages can flip images of distant ships upside down or stretch them into ghostly towers, a spectacle known as the Fata Morgana. All of these effects show how weather interacts not only with air and water, but with light itself, turning the sky into a theater of refraction, reflection, and scattering. Now, let's shift from light to sound in the atmosphere. Sound travels as waves through molecules, and the atmosphere is full of them. From the roar of thunder to the whistle of wind around corners, air carries vibrations across great distances, but conditions can amplify or dampen those sounds. For instance, on a cool evening with calm winds, sound can carry farther because the air near the ground is cooler than the air above, creating an inversion. This bends sound waves back downward, keeping them close to the surface instead of letting them dissipate upward. That's why distant trains or dogs barking can sound unusually loud at night. Thunder itself is the most dramatic weather-related sound. It results from the rapid expansion of superheated air around a lightning bolt. The shockwave travels outward as a booming crack or rolling rumble, depending on distance and terrain. Closer strikes produce sharp cracks, distant ones roll for several seconds. The atmosphere also creates quieter sounds, subtle whistles, rustles, or eerie hums. Strong winds around buildings can generate moaning tones, while natural features like canyons and valleys act as amplifiers or echoes. Even the whisper of snow underfoot is an atmospheric story, tiny crystals compressing, breaking, and squeaking beneath your steps. Weather not only produces sound, it can also silence it. Falling snow absorbs vibrations, blanketing landscapes in quiet. This hush is part of what makes winter snowfall feel so tranquil. From light shows in the sky to the music of storms and silence, the atmosphere is both an artist and a performer. It dazzles with rainbows, halos, and mirages while roaring with thunder or softening the world with snow's muffled calm. Now, let's turn to long-term patterns, climate, and how they differ from day-to-day weather. Weather is immediate, what's happening in the atmosphere at a given place and time. Climate is broader, the average of weather patterns over decades or centuries. While a rainstorm might drench a city this afternoon, the climate describes whether that region is usually wet or dry, hot or cold across years. Climate zones emerge from the interaction of sunlight, geography, and atmospheric circulation. Near the equator, abundant sunlight and rising air create tropical climates, with year-round warmth and heavy rainfall. Moving poleward, subtropical zones become drier, hosting deserts where sinking air suppresses precipitation. Temperate regions in mid-latitudes experience seasonal swings, while polar climates remain cold and harsh, dominated by ice and long winters. Mountains complicate this map. They block moisture-laden winds, creating rain shadows on their leeward sides, where deserts often form. Coastal regions, in contrast, benefit from the moderating influence of oceans, which store and release heat slowly, softening seasonal extremes. Climates can shift over time. Natural cycles like El Niño and La Niña alter ocean temperatures and atmospheric patterns every few years, redistributing rainfall and influencing storm tracks. Longer-term changes come from shifts in Earth's orbit, volcanic eruptions, or solar variation. In recent centuries, human activities, especially the burning of fossil fuels, have accelerated climate change, raising global temperatures and altering rainfall, storm intensity, and sea levels. Understanding climate is essential not only for science, but for survival. Agriculture depends on predictable seasonal patterns. Cities plan infrastructure around average rainfall, heat, and storms. Wildlife evolves to match long-term conditions. When those conditions shift, the consequences ripple through ecosystems, economies, and human lives. The story of weather cannot be told without acknowledging climate, for every sunny afternoon and winter storm exists within that broader framework. Together, they form the rhythms of our planet's living atmosphere. When we study weather, it's tempting to focus only on what happens close to the ground: rain, sunshine, wind, and storms. But the truth is, the higher layers of the atmosphere play just as critical a role. To really understand weather, we have to look upward, into the grand structure of Earth's protective shell. The atmosphere is layered like an invisible cake, each section with its own traits, behaviors, and importance. The lowest layer, where weather unfolds, is the troposphere. It extends from the surface up to around 7 miles at mid-latitudes, but varies depending on geography. Higher over the equator, lower over the poles. In the troposphere, temperatures generally drop as you ascend. This vertical gradient powers rising and sinking motions, driving storms, winds, and cloud formation. Virtually all the weather phenomena we observe, clouds, rain, snow, tornadoes, hurricanes, occur here. The air is dense enough to sustain life and rich with moisture. Jet airplanes often fly near the top of this layer, skimming just beneath the boundary to avoid turbulence. That boundary is called the tropopause, marking the ceiling of the troposphere. Above it lies the stratosphere, stretching to about 30 miles above the surface. Unlike the troposphere, the stratosphere warms as altitude increases. This reversal happens because of the ozone layer, which absorbs ultraviolet radiation from the sun. By converting harmful UV rays into heat, the ozone layer not only shields life below, but also creates a unique thermal structure. The stratosphere is calmer than the turbulent troposphere, with less vertical mixing. This makes it ideal for long-distance flights. Weather balloons often drift into it, collecting valuable data. The stratosphere also hosts remarkable phenomena like polar stratospheric clouds, which shimmer with iridescent colors during polar winters. Above the stratosphere lies the mesosphere, extending up to 50 miles high. Temperatures here plunge again, dropping to some of the coldest anywhere in Earth's atmosphere. The mesosphere is where meteors often burn up, their fiery streaks lighting the night sky as they collide with air molecules. Despite its beauty, the mesosphere remains difficult to study, too high for airplanes and balloons, too low for satellites to orbit efficiently. Next comes the thermosphere, stretching hundreds of miles upward. Here, solar radiation excites atoms, raising temperatures dramatically, though not in a way humans would feel. The air is so thin that heat energy is sparse despite molecules vibrating furiously. The thermosphere hosts the auroras, brilliant curtains of green, red, and purple light caused when charged particles from the sun interact with atmospheric gases. The International Space Station orbits within this realm, circling Earth against the backdrop of shimmering auroral displays. Beyond the thermosphere lies the exosphere, the outermost transition to space. Here, air molecules are so widely spaced that they can drift away into the void. Satellites orbit in this tenuous zone, experiencing faint traces of atmospheric drag. Each of these layers contributes to weather and climate in its own way. The troposphere is the stage for daily patterns. The stratosphere regulates radiation. The upper layers act as shields, protecting us from meteors and solar wind. Together, they form Earth's atmospheric armor, a fragile yet vital blanket. Now, let's examine one of the atmosphere's most mysterious features, the jet streams. Jet streams are narrow bands of fast-moving air that snake around the globe at the top of the troposphere. They were first discovered by pilots during World War II, who noticed that some flights sped up or slowed dramatically depending on altitude and direction. These winds can reach speeds of over 200 miles per hour, acting like atmospheric rivers. There are two primary jet streams in each hemisphere: the polar jet, near 50 to 60 degrees latitude, and the subtropical jet, closer to 30 degrees. They form because of temperature differences between air masses. The sharp boundary between cold polar air and warm tropical air sets up steep pressure gradients, which, combined with Earth's rotation, drive the streams. Jet streams meander like rivers, sometimes flowing smoothly, sometimes forming great waves. When they dip southward, they can drag cold polar air into temperate regions, causing frigid outbreaks. When they bulge northward, they pull warm tropical air poleward, fueling heat waves. Their influence is profound. Storm systems often travel along jet stream paths, using them like highways. A wavy jet stream can stall, trapping weather patterns in place. This stalling explains why some regions experience prolonged rain, droughts, or heat spells. Climate change appears to be influencing jet stream behavior. As the Arctic warms faster than lower latitudes, the temperature contrast that drives the polar jet weakens. Some studies suggest this makes the stream more prone to extreme meanders, though research continues. Beneath these powerful currents lies another hidden driver of weather: ocean-atmosphere interaction. The oceans cover 70% of Earth's surface and act as giant heat reservoirs. They absorb sunlight, store warmth, and release it slowly. This interaction between ocean and atmosphere sets the rhythm for many climate systems. The most famous of these is El Niño Southern Oscillation, ENSO. In normal years, trade winds blow warm surface water westward across the Pacific, piling it near Asia, while cooler waters rise near South America. In El Niño years, those winds weaken, warm water sloshes eastward, and global weather patterns shift. South America may experience flooding, while regions in Asia endure drought. North America often sees wetter winters in the south and milder conditions in the north. In contrast, La Niña strengthens the trade winds, amplifying the normal pattern. Cold water surges along South America's coast, storms intensify in Asia, and droughts may strike the western United States. Both phases ripple across the planet, influencing hurricanes, monsoons, and agriculture. Another player is the Atlantic Multidecadal Oscillation, AMO, a long-term fluctuation in North Atlantic Sea surface temperatures. Warm phases correlate with more active hurricane seasons, while cool phases suppress activity. Similarly, the Indian Ocean Dipole, IOD, alternates between warm and cool phases, shaping rainfall from East Africa to Australia. Currents also matter. The Gulf Stream, for instance, transports warm tropical waters northward, moderating climates in Europe. Without it, winters there would be harsher, resembling Canada's latitude. Deep beneath the surface, global conveyor belts of water, driven by temperature and salinity differences, circulate energy around the planet, balancing heat across hemispheres. Together, the atmosphere and ocean form a coupled system. Storms draw strength from warm seas, while winds steer currents. Any shift in one echoes through the other. This delicate dance sustains Earth's climate, but also introduces variability and surprises. Let's move from oceans back to the land, specifically to how geography sculpts local weather. Mountains, valleys, and coastlines are not just backdrops, they actively shape atmospheric behavior. As moist winds hit a mountain range, they are forced upward, cooling and condensing into clouds. This orographic lifting produces heavy rain on the windward side, nurturing lush forests. On the leeward side, air descends, warms, and dries, creating rain shadows where deserts often appear. The Andes, Cascades, and Himalayas all illustrate this effect dramatically. Valleys channel air, enhancing winds or trapping fog. Cold, dense air often sinks into low-lying basins at night, creating frost pockets. Cities in valleys can experience persistent smog when stagnant air fails to disperse pollutants. Coastlines' moderate temperature swings, as oceans absorb heat slowly and release it gradually. Inland regions, in contrast, endure greater extremes, scorching summers, freezing winters. Sea breezes cool coastal towns by day, while land breezes reverse the flow at night. Even small-scale geography matters. Urban areas create heat islands, where concrete and asphalt absorb sunlight, raising temperatures several degrees higher than rural surroundings. This not only influences comfort but also energy demand, storm development, and air quality. In every corner of the globe, geography intertwines with atmosphere and ocean, creating distinctive local climates. From foggy coasts to arid plateaus, from storm-battered islands to fertile plains, Earth's surface shapes the personality of its skies. When most people think of dramatic weather, they imagine storms, those powerful bursts of energy that transform calm skies into spectacles of rain, lightning, thunder, and wind. Storms remind us that the atmosphere is alive, constantly moving energy from one place to another. The simplest type of storm is the thunderstorm. These form when warm, moist air near the surface rises rapidly into cooler regions of the atmosphere. As it rises, the moisture condenses into clouds, releasing heat that fuels the process further. This positive feedback builds towering cumulonimbus clouds, often stretching miles into the sky. Thunderstorms usually develop in 3 stages. The cumulus stage begins with upward growth as air rises and forms puffy clouds. Next comes the mature stage, when the storm is fully developed, producing heavy rain, thunder, lightning, strong winds, and sometimes hail. Finally, the dissipating stage occurs when downdrafts dominate, cutting off the storm's supply of warm, moist air. The storm weakens and rains itself out. Lightning, the hallmark of thunderstorms, is a massive electrical discharge. Within the storm cloud, collisions between ice particles and water droplets separate charges, creating regions of positive and negative energy. When the difference becomes great enough, electricity leaps across the gap, either within the cloud, between clouds, or down to the ground. The sudden superheating of air along this path produces thunder, a sound wave that cracks or rumbles depending on distance and terrain. Most lightning bolts strike within clouds, but cloud-to-ground strikes are the most dangerous. They can ignite fires, damage buildings, and injure or kill living beings. On average, Earth experiences around 8 million lightning strikes each day, a reminder of how frequent and powerful this phenomenon is. Thunderstorms can produce hail, formed when strong updrafts lift raindrops into freezing regions of the cloud. As the droplets are tossed up and down, layers of ice accumulate until they become heavy enough to fall. Some hailstones grow larger than baseballs, wreaking havoc on crops, roofs, and vehicles. Another threat from thunderstorms is tornadoes. These violent, rotating columns of air descend from the base of a thunderstorm to the ground, packing winds that can exceed 200 miles per hour. Tornado formation is still not fully understood, but it typically involves intense wind shear, changes in wind direction and speed with altitude, that creates horizontal rotation. Updrafts tilt this rotation vertically, forming the funnel. Tornadoes vary widely in strength and size. The enhanced Fujita scale ranks them from EF0, causing light damage, to EF5, capable of leveling well-built structures. While they last only minutes, their concentrated power can devastate entire towns. The United States sees the highest number globally, particularly in the region nicknamed Tornado Alley, though they occur on nearly every continent. Beyond thunderstorms and tornadoes, the atmosphere also spawns tropical cyclones, known as hurricanes in the Atlantic, typhoons in the Pacific, and simply cyclones elsewhere. These immense systems draw energy from warm ocean waters. When surface temperatures exceed about 80 degrees Fahrenheit, heat and moisture rise, condensing into clouds and releasing latent heat. This fuels more rising air, lowering surface pressure and creating a self-sustaining cycle. Tropical cyclones feature distinct parts. At the center is the eye, a calm region of sinking air often marked by clear skies. Surrounding it lies the eye wall, a ring of intense thunderstorms producing the strongest winds and heaviest rain. Spiral rain bands extend outward, bringing squalls hundreds of miles from the core. These storms are ranked by the Saffir-Simpson scale, from Category 1 with winds just above 74 miles per hour to Category 5 with sustained winds over 157. Beyond wind, their greatest danger is often storm surge, a rise in sea level driven by wind and low pressure, which can flood coastal regions. Torrential rains add inland flooding to the hazards. While cyclones cause destruction, they also play a natural role in balancing Earth's heat. By transporting energy from tropics toward higher latitudes, they contribute to the global circulation. Still, for those in their paths, preparation and warning systems are essential. Not all storms involve the tropics. Mid-latitude cyclones, common in temperate regions, form along boundaries between warm and cold air masses. They bring sweeping fronts, widespread precipitation, and strong winds. These systems can stretch for thousands of miles, influencing weather across continents. Winter storms bring another set of challenges. When moist air collides with freezing conditions, snow and ice blanket landscapes. Blizzards combine heavy snowfall with winds over 35 miles per hour, reducing visibility to near zero. Travel grinds to a halt, power lines snap under weight, and extreme cold endangers lives. Ice storms are particularly treacherous. Unlike snow, freezing rain coats every surface with glaze, roads, trees, wires, creating hazards that linger long after precipitation ends. Such storms can cripple infrastructure, sometimes leaving communities without power for weeks. Other storm types include dust storms, which occur in arid regions when strong winds lift sand and silt into the air, reducing visibility and carrying particles over long distances. The Sahara regularly sends plumes of dust across the Atlantic, fertilizing soils in the Amazon basin. Derechos, widespread windstorms associated with lines of thunderstorms, can flatten forests and damage cities in just a few hours. Each storm type illustrates the atmosphere's ability to focus immense energy. From the fleeting flash of lightning to the sprawling reach of a hurricane, storms demonstrate the atmosphere's restless drive to balance heat, moisture, and motion. But storms are not purely destructive. They also serve ecological roles. Lightning fixes nitrogen in soils, enriching them for plants. Floods replenish wetlands and distribute nutrients. Snowpack provides crucial water supplies for rivers and agriculture. Even destructive winds can clear old forests, making way for new growth. Humans, of course, have adapted to storms with shelters, forecasting, and technology. Satellites watch from space, radars peer inside clouds, and computer models predict paths and intensities. Warning systems save lives, though challenges remain in communicating urgency and reaching vulnerable populations. Storms have also shaped culture and mythology. Ancient peoples often saw thunder as the voice of gods, Zeus hurling lightning bolts, Thor wielding his hammer, or spirits battling in the heavens. Modern science has replaced these tales with physics, but the awe remains. Few experiences rival the sight of a thunderstorm rolling across the horizon or the roar of surf under a hurricane's winds. Now let's turn to another essential component of weather: wind. Wind is simply air in motion, but its effects are anything but simple. It shapes climates, sculpts landscapes, powers storms, and influences human activity from sailing to energy generation. Wind arises because of differences in air pressure, flowing from high to low, deflected by Earth's rotation. On a global scale, wind organizes into belts. Near the equator, intense heating drives rising air, creating low pressure. This air spreads poleward aloft, then sinks around 30 degrees latitude, producing subtropical highs. The surface winds returning toward the equator become the trade winds, steady easterlies that guided explorers and traders for centuries. Between 30 and 60 degrees latitude lie the westerlies, prevailing winds blowing from west to east. These drive weather systems across mid-latitudes, including much of North America and Europe. Closer to the poles, polar easterlies sweep cold air outward. Where westerlies meet polar easterlies lies the polar front, a battleground for storms. Regional winds add variety. Monsoons reverse seasonally, bringing wet summers and dry winters across South Asia and Africa. Chinooks descend the leeward sides of mountains, warming dramatically as they compress. Santa Anas in California funnel dry, hot air toward the coast, fanning wildfires. Winds also create local breezes. Along coasts, sea breezes develop by day as land heats faster than water, drawing cool air inland. At night, land breezes flow outward as the process reverses. In valleys, mountain slopes trigger daily upslope and downslope winds, circulating air predictably. The power of wind extends beyond weather into geology and human history. Wind erosion carves desert dunes, shapes rock formations, and carries dust across oceans. Ancient civilizations harnessed wind with sails, spreading cultures and trade. Today, modern turbines transform wind into renewable electricity, a vital piece of energy transitions. Yet wind can also bring danger. Strong gusts topple trees, damage buildings, and fuel wildfires. Hurricanes and tornadoes showcase wind at its most extreme. Understanding and forecasting wind remains central to meteorology, as it connects every scale of atmospheric motion. Wind, storms, rain, snow, all weave together into the intricate fabric of weather. Each phenomenon is part of Earth's great balancing act, redistributing heat and energy across the globe. As chaotic as weather may seem, underlying patterns tie it together. To grasp the full scope of weather, it's not enough to study individual storms, winds, or clouds. We must step back and see how everything interlocks into larger cycles. Weather is not random chaos. It is a system driven by solar energy, Earth's rotation, geography, and the constant flow of air and water. One of the key concepts is the water cycle, the endless movement of water between the atmosphere, land, and oceans. This cycle powers much of the weather we experience. It begins with evaporation, as sunlight warms oceans, lakes, and rivers, turning liquid into vapor. Plants add to this through transpiration, releasing moisture from leaves. Together, these processes feed the atmosphere with water vapor. Once airborne, water vapor rises, cools, and condenses into clouds. Tiny droplets cluster around dust or salt particles, forming visible masses. When droplets grow large enough, they fall as precipitation, rain, snow, sleet, or hail, returning water to the surface. Some soaks into the ground, replenishing aquifers. Some runs into rivers, feeding lakes and seas. From there, evaporation begins anew. This recycling of water is crucial for life. It irrigates crops, fills reservoirs, and sustains ecosystems. It also drives energy transfer, since condensation releases latent heat that fuels storms. Without the water cycle, weather as we know it would not exist. Another crucial engine of weather is solar energy. The sun provides uneven heating across Earth's surface, strongest at the equator, weakest at the poles. This imbalance creates pressure differences, which set air in motion. The circulation of air and oceans works tirelessly to redistribute heat, striving for equilibrium. This global circulation organizes into three main cells per hemisphere. Near the equator lies the Hadley cell, where warm air rises, moves poleward, sinks around 30 degrees latitude, and returns as surface trade winds. Between 30 and 60 degrees, the Ferrel cell spins in the opposite direction, driven by interactions between westerlies and polar air. Finally, the polar cell circulates cold air near the poles. These cells are not perfect loops, but they describe the general flow of energy. Overlaying these cells are jet streams, monsoons, and ocean currents, all fine-tuning the balance. The result is a complex but organized system that explains why deserts form in some regions, rainforests in others, and why certain coasts enjoy mild climates while interiors swing between extremes. Ocean currents deserve special attention. They are often called the conveyor belts of the planet, transporting heat thousands of miles. Warm surface currents like the Gulf Stream move poleward, keeping nearby regions temperate. Cold currents like the Humboldt or California currents bring nutrient-rich water up from the depths, feeding marine life but chilling coastal climates. Beneath the surface flows the thermohaline circulation, driven by differences in temperature and salinity. In polar regions, water cools, grows denser, and sinks, pulling warm water northward to replace it. This slow-moving conveyor regulates global climate over centuries. Any disruption, such as melting ice altering salinity, can ripple through the system with vast consequences. All these cycles, water, energy, air, and ocean, interweave to sustain life. They also create variability. The same processes that bring fertile rains one year can unleash drought the next. Speaking of drought, let's explore extreme weather events beyond storms. Drought occurs when precipitation falls below average for an extended period, stressing crops, ecosystems, and water supplies. Unlike sudden storms, droughts creep slowly, sometimes unnoticed until reservoirs shrink and fields wither. They can last months or years, reshaping entire regions. The opposite extreme is flooding. Rivers can overflow after prolonged rains, snowmelt, or sudden downpours. Coastal floods arise from storm surges and tides. Flash floods strike with little warning when intense rain overwhelms dry ground or urban pavement. Water, though life-giving, becomes destructive when unleashed too quickly. Another hazard is heat waves, extended periods of extreme heat. They stress human health, strain power grids and dry soils, sometimes fueling wildfires. Urban heat islands worsen their impact, as concrete holds warmth overnight, preventing relief. Conversely, cold waves sweep polar air into lower latitudes, plunging regions into frigid conditions. Frost damages crops, ice clogs rivers, and heating demands rise. In both heat and cold, vulnerable populations face the greatest risk. Wildfires, though not weather themselves, often link to atmospheric conditions. Prolonged heat, drought, and wind create tinderbox environments. Once sparked, flames spread rapidly, generating their own winds and even fire-induced clouds that can spawn lightning. Smoke plumes travel vast distances, altering air quality and even weather in downwind areas. Extreme weather has always existed, but modern observation shows trends toward greater intensity in some events. Rising global temperatures amplify heat waves, boost evaporation that fuels storms, and shift precipitation patterns. Sea level rise increases the reach of storm surges. The interplay between natural variability and human-driven change is a central focus of today's climate science. Forecasting extreme events remains a challenge. Meteorologists use satellites, radars, and models to predict conditions, but uncertainties remain, especially with storms that develop rapidly. Even with accurate forecasts, communicating urgency is critical. Warnings must reach communities clearly, early, and in a form people trust. Technology has revolutionized how we monitor weather. Satellites provide global coverage, tracking clouds, temperatures, winds, and moisture. They allow us to watch hurricanes spin across oceans days before landfall or monitor drought from space. Polar orbiting satellites scan the entire planet, while geostationary satellites hover over fixed points, offering continuous views. Radar systems penetrate clouds, mapping rainfall intensity and storm structure. Doppler radar detects wind speeds, revealing rotation that hints at tornado formation. Ground networks of sensors measure temperature, humidity, and pressure. Weather balloons ascend twice daily from hundreds of locations, feeding upper air data into models. Computer models are the backbone of modern forecasting. They divide the atmosphere into three-dimensional grids, solving equations that describe fluid motion, thermodynamics, and radiation. Supercomputers crunch billions of calculations, simulating future conditions based on current data. Models vary in resolution and scope, some focus globally, others regionally. Despite their sophistication, models are imperfect. The atmosphere is chaotic, meaning tiny differences in starting conditions can lead to very different outcomes. That's why forecasts become less reliable the farther they extend. Short-term predictions are often precise, but beyond a week, uncertainty grows. Seasonal forecasts rely more on patterns like El Niño than exact day-to-day weather. To improve accuracy, meteorologists run ensemble forecasts, multiple simulations with slightly different initial conditions. By comparing results, they estimate probabilities. Instead of saying it will definitely rain tomorrow, forecasts might state a 70% chance, reflecting uncertainty. Communication is as important as calculation. A perfect model is useless if people ignore warnings or misunderstand them. Meteorologists refine how they present forecasts, balancing precision with clarity. In many cases, simple language, "take shelter now," saves more lives than technical detail. The history of weather forecasting is remarkable. Ancient cultures relied on observation, red skies, animal behavior, or cloud shapes. Sailors memorized sayings like "red sky at night, sailor's delight." In the 19th century, telegraphs allowed data sharing across regions, enabling the first large-scale forecasts. Radar in World War II revealed storm structures, and satellites in the 20th century transformed global monitoring. Today, we live in the most informed era in history, though challenges remain. Forecasting also matters beyond safety. Farmers plan planting and harvesting around expected rainfall. Energy companies anticipate demand during heat or cold waves. Airlines adjust routes for jet streams. Everyday life, from outdoor events to commutes, depends on timely forecasts. The atmosphere may seem unpredictable, but human ingenuity continues to unlock its patterns, turning mystery into manageable knowledge. Still, humility is necessary. Forecasting improves, but surprises persist. A storm may veer unexpectedly, rainfall may exceed estimates, or drought may linger despite predictions of relief. These remind us that nature retains its independence, despite our best models. Looking forward, advances in technology, more powerful computers, denser sensor networks, and artificial intelligence promise sharper forecasts. Yet even as precision grows, the fundamental goal remains the same: to protect lives, property, and livelihoods from the shifting moods of the sky. To grasp the full scope of weather, it's not enough to study individual storms, winds, or clouds. We must step back and see how everything interlocks into larger cycles. Weather is not random chaos. It is a system driven by solar energy, Earth's rotation, geography, and the constant flow of air and water. One of the key concepts is the water cycle, the endless movement of water between the atmosphere, land, and oceans. This cycle powers much of the weather we experience. It begins with evaporation, as sunlight warms oceans, lakes, and rivers, turning liquid into vapor. Plants add to this through transpiration, releasing moisture from leaves. Together, these processes feed the atmosphere with water vapor. Once airborne, Water vapor rises, cools, and condenses into clouds. Tiny droplets cluster around dust or salt particles, forming visible masses. When droplets grow large enough, they fall as precipitation, rain, snow, sleet, or hail, returning water to the surface. Some soaks into the ground, replenishing aquifers. Some runs into rivers, feeding lakes and seas. From there, evaporation begins anew. This recycling of water is crucial for life. It irrigates crops, fills reservoirs, and sustains ecosystems. It also drives energy transfer, since condensation releases latent heat that fuels storms. Without the water cycle, weather as we know it would not exist. Another crucial engine of weather is solar energy. The sun provides uneven heating across Earth's surface, strongest at the equator, weakest at the poles. This imbalance creates pressure differences, which set air in motion. The circulation of air and oceans works tirelessly to redistribute heat, striving for equilibrium. This global circulation organizes into three main cells per hemisphere. Near the equator lies the Hadley cell, where warm air rises, moves poleward, sinks around 30 degrees latitude, and returns as surface trade winds. Between 30 and 60 degrees, the Ferrel cell spins in the opposite direction, driven by interactions between westerlies and polar air. Finally, the polar cell circulates cold air near the poles. These cells are not perfect loops, but they describe the general flow of energy. Overlaying these cells are jet streams, monsoons, and ocean currents, all fine-tuning the balance. The result is a complex but organized system that explains why deserts form in some regions, rainforests in others, and why certain coasts enjoy mild climates while interiors swing between extremes. Ocean currents deserve special attention. They are often called the conveyor belts of the planet, transporting heat thousands of miles. Warm surface currents like the Gulf Stream move poleward, keeping nearby regions temperate. Cold currents like the Humboldt or California currents bring nutrient-rich water up from the depths, feeding marine life but chilling coastal climates. Beneath the surface flows the thermohaline circulation, driven by differences in temperature and salinity. In polar regions, water cools, grows denser, and sinks, pulling warm water northward to replace it. This slow-moving conveyor regulates global climate over centuries. Any disruption, such as melting ice altering salinity, can ripple through the system with vast consequences. All these cycles, water, energy, air, and ocean, interweave to sustain life. They also create variability. The same processes that bring fertile rains one year can unleash drought the next. Speaking of drought, let's explore extreme weather events beyond storms. Drought occurs when precipitation falls below average for an extended period, stressing crops, ecosystems, and water supplies. Unlike sudden storms, droughts creep slowly, sometimes unnoticed until reservoirs shrink and fields wither. They can last months or years, reshaping entire regions. The opposite extreme is flooding. Rivers can overflow after prolonged rains, snowmelt, or sudden downpours. Coastal floods arise from storm surges and tides. Flash floods strike with little warning, when intense rain overwhelms dry ground or urban pavement. Water, though life-giving, becomes destructive when unleashed too quickly. Another hazard is heat waves, extended periods of extreme heat. They stress human health, strain power grids, and dry soils, sometimes fueling wildfires. Urban heat islands worsen their impact, as concrete holds warmth overnight, preventing relief. Conversely, cold waves sweep polar air into lower latitudes, plunging regions into frigid conditions. Frost damages crops, ice clogs rivers, and heating demands rise. In both heat and cold, vulnerable populations face the greatest risk. Wildfires, though not weather themselves, often linked to atmospheric conditions. Prolonged heat, drought, and wind create tinderbox environments. Once sparked, flames spread rapidly, generating their own winds and even fire-induced clouds that can spawn lightning. Smoke plumes travel vast distances, altering air quality and even weather in downwind areas. Extreme weather has always existed, but modern observation shows trends toward greater intensity in some events. Rising global temperatures amplify heat waves, boost evaporation that fuels storms, and shift precipitation patterns. Sea level rise increases the reach of storm surges. The interplay between natural variability and human-driven change is a central focus of today's climate science. Forecasting extreme events remains a challenge. Meteorologists use satellites, radars, and models to predict conditions, but uncertainties remain, especially with storms that develop rapidly. Even with accurate forecasts, communicating urgency is critical. Warnings must reach communities clearly, early, and in a form people trust. Technology has revolutionized how we monitor weather. Satellites provide global coverage, tracking clouds, temperatures, winds, and moisture. They allow us to watch hurricanes spin across oceans days before landfall, or monitor drought from space. Polar orbiting satellites scan the entire planet, while geostationary satellites hover over fixed points, offering continuous views. Radar systems penetrate clouds, mapping rainfall intensity and storm structure. Doppler radar detects wind speeds, revealing rotation that hints at tornado formation. Ground networks of sensors measure temperature, humidity, and pressure. Weather balloons ascend twice daily from hundreds of locations, feeding upper-air data into models. Computer models are the backbone of modern forecasting. They divide the atmosphere into three-dimensional grids, solving equations that describe fluid motion, thermodynamics, and radiation. Supercomputers crunch billions of calculations, simulating future conditions based on current data. Models vary in resolution and scope. Some focus globally, others regionally. Despite their sophistication, models are imperfect. The atmosphere is chaotic, meaning tiny differences in starting conditions can lead to very different outcomes. That's why forecasts become less reliable the farther they extend. Short-term predictions are often precise, but beyond a week, uncertainty grows. Seasonal forecasts rely more on patterns like El Niño than exact day-to-day weather. To improve accuracy, meteorologists run ensemble forecasts, multiple simulations with slightly different initial conditions. By comparing results, they estimate probabilities. Instead of saying it will definitely rain tomorrow, forecasts might state a 70% chance, reflecting uncertainty. Communication is as important as calculation. A perfect model is useless if people ignore warnings or misunderstand them. Meteorologists refine how they present forecasts, balancing precision with clarity. In many cases, simple language, "take shelter now," saves more lives than technical detail. The history of weather forecasting is remarkable. Ancient cultures relied on observation, red skies, animal behavior, or cloud shapes. Sailors memorized sayings like "red sky at night, sailor's delight." In the 19th century, telegraphs allowed data sharing across regions, enabling the first large-scale forecasts. Radar in World War II revealed storm structures, and satellites in the 20th century transformed global monitoring. Today, we live in the most informed era in history, though challenges remain. Forecasting also matters beyond safety. Farmers plan planting and harvesting around expected rainfall. Energy companies anticipate demand during heat or cold waves. Airlines adjust routes for jet streams. Everyday life, from outdoor events to commutes, depends on timely forecasts. The atmosphere may seem unpredictable, but human ingenuity continues to unlock its patterns, turning mystery into manageable knowledge. Still, humility is necessary. Forecasting improves, but surprises persist. A storm may veer unexpectedly, rainfall may exceed estimates, or drought may linger despite predictions of relief. These remind us that nature retains its independence despite our best models. Looking forward, advances in technology, more powerful computers, denser sensor networks, and artificial intelligence promise sharper forecasts. Yet even as precision grows, the fundamental goal remains the same: to protect lives, property, and livelihoods from the shifting moods of the sky. Weather not only shapes the natural world but also directs the course of human history. From agriculture to warfare, trade to exploration, the atmosphere has always been a decisive factor in human destiny. To understand our relationship with weather is to understand much of civilization itself. Agriculture, the foundation of settled life, depends directly on climate and weather. Early societies flourished where seasonal rains and fertile soils provided reliable harvests. The Nile's annual floods sustained Egypt, while the monsoons supported India and Southeast Asia. In contrast, prolonged droughts contributed to the decline of civilizations like the Maya. Even today, farmers live at the mercy of rainfall patterns, frosts, and storms. Advances like irrigation and forecasting reduce risk, but dependence on weather never disappears. Trade and exploration have also been bound to winds and currents. For centuries, sailors relied on predictable trade winds and monsoons to cross oceans. The ability to navigate these atmospheric highways determined which nations rose to maritime power. Without understanding prevailing winds, global exploration would have been impossible. Wars, too, bear the fingerprints of weather. Napoleon's invasion of Russia faltered under brutal cold, with frost and snow destroying more soldiers than battle did. During World War II, the D-Day invasion depended on forecasts of tides, winds, and skies. A small window of favorable weather allowed the Allies to launch, altering the war's outcome. At times, fog has hidden armies, rains have bogged down campaigns, and storms have scattered fleets. On a personal scale, weather influences daily life in countless ways. The clothes we wear, the foods we eat, and the energy we consume all reflect atmospheric conditions. Heat drives demand for air conditioning, cold drives heating needs. Heavy snow halts transportation. Hurricanes reshape economies overnight. Beyond practicality, weather affects mood. Sunshine lifts spirits while gray skies dampen them. Culturally, weather inspires art, literature, and mythology. Poets describe storms as symbols of passion or turmoil. Painters capture the shifting light of clouds and sunsets. Music mimics thunder and rain. In myth, gods of weather command awe: Zeus, Thor, Rajan, and others. Even today, weather forecasts dominate conversations, shaping social interactions. Scientific study of weather, meteorology, is relatively young compared to humanity's long history of observation. Early cultures tracked seasonal cycles with calendars and monuments like Stonehenge. Aristotle wrote one of the first treatises on weather, though much of it was speculation. The invention of instruments like barometers, thermometers, and anemometers in the 17th century transformed weather from mystery to measurable science. The 19th century brought a revolution with telegraphs. For the first time, observers could share data quickly across regions, allowing broader forecasting. Governments established meteorological services, standardizing observations and issuing warnings. The 20th century added aircraft, radar, and satellites, giving unprecedented perspectives on clouds and storms. Today, meteorology blends data from ground networks, sky observations, and computer models, making forecasts increasingly reliable. Yet even with science's advances, weather retains its unpredictability. Forecasts grow less certain with time because the atmosphere is chaotic. A small difference in initial conditions can create very different outcomes, a principle known as the butterfly effect. Thus, while short-term forecasts are highly accurate, long-term predictions must lean on probabilities and patterns rather than specifics. Climate science extends meteorology into broader timescales. By studying tree rings, ice cores, sediments, and fossils, researchers reconstruct past climates, revealing cycles of warming and cooling. These records provide perspective on modern changes, showing how unusual today's rapid warming is compared to natural variations. Weather and climate knowledge now intertwine with policy and planning. Cities design drainage systems for heavier rains, coastal communities prepare for rising seas, and nations coordinate disaster responses. Insurance companies assess risk based on storm frequency, while militaries plan around weather-sensitive technologies. Even space exploration considers weather, as launches depend on clear skies, calm winds, and lightning-free conditions. Looking to the future, meteorology faces both opportunities and challenges. Technology continues to expand the limits of observation. New generations of satellites capture sharper images, track moisture at finer scales, and measure winds across oceans. Networks of automated sensors deliver real-time data, while drones and high-altitude aircraft sample storms directly. Supercomputers simulate atmospheric flows at higher resolution than ever before, narrowing uncertainties in forecasts. Artificial intelligence is also entering meteorology. Machine learning analyzes vast data sets, finding patterns humans might overlook. These systems assist in recognizing storm formation, refining predictions of rainfall, or estimating risks of floods and droughts. Still, AI cannot replace the fundamental physics of the atmosphere. It supplements, not substitutes, traditional modeling. Public communication remains vital. Even the most accurate forecast fails if people don't act on it. Meteorologists must present information in ways that encourage trust and quick response. False alarms erode credibility, but failing to warn can cost lives. Balancing precision, clarity, and urgency is one of the field's greatest responsibilities. Beyond science and society, there is the human experience of weather itself. Few things stir the senses like standing in a thunderstorm, hearing thunder echo, and watching lightning crack the sky. The first snowfall transforms landscapes into silence and wonder. Sunsets paint the sky with shifting hues, reminding us of daily cycles. These moments connect us to forces greater than ourselves. For some, weather provides a livelihood: farmers, fishers, pilots, sailors, and meteorologists themselves. For others, it is simply the backdrop of life. Yet whether admired, endured, or feared, weather is universal. It shapes food, shelter, and survival. It offers beauty and danger in equal measure. As we reflect on weather, one truth emerges. It is both ordinary and extraordinary. Ordinary because it surrounds us daily, influencing every decision from clothing to travel. Extraordinary because it links us to the cosmos, carrying energy from the sun, interacting with oceans, sculpting landscapes, and determining the fate of species. The Sleepy Narrator reminds us that weather is not just science to memorize. It is a story unfolding around us every day. From the whisper of a breeze to the roar of a cyclone, from the sparkle of frost to the crash of waves under storm surge, weather is poetry written in air and water. To listen to it is to connect with the planet on its deepest level. Our relationship with weather continues to evolve. We predict it, prepare for it, and sometimes try to influence it. Cloud seeding experiments attempt to enhance rainfall. Urban planners design heat-resistant cities. Farmers use forecasts to time irrigation. Pilots adjust routes to avoid turbulence. Yet control remains limited. Weather is too vast, too complex to bend entirely to human will. Perhaps that is for the best. Weather humbles us, reminding us that despite technology and power, we remain part of Earth's system. Our survival depends not on conquering the atmosphere, but on respecting and adapting to it. As much as weather shapes our daily lives, it also drives the story of Earth itself. Over millions of years, the atmosphere has shifted through extremes: scorching heat, ice ages, storms beyond imagination. By studying these patterns, we see weather not just as fleeting events, but as threads in Earth's long narrative. Consider the ice ages. Over the last 2 million years, vast ice sheets advanced and retreated repeatedly. Entire continents lay under miles of ice. These shifts were tied to orbital variations, changes in greenhouse gases, and ocean circulation. Glaciers carved valleys, deposited sediments, and shaped modern landscapes. When the ice retreated, it left behind fertile soils that nourished civilizations. Earlier still, climates swung to hotter extremes. During the Cretaceous period, for example, carbon dioxide levels were far higher, and dinosaurs roamed forests that extended nearly to the poles. No permanent ice existed, and sea levels stood hundreds of feet higher than today. Such eras remind us that Earth's atmosphere has never been static. It evolves constantly, influenced by both internal processes and cosmic factors. Weather has even reached planetary scales of transformation. The so-called Great Oxidation Event, billions of years ago, saw cyanobacteria release oxygen into the atmosphere, forever changing its chemistry. This altered not only weathering of rocks and ocean chemistry, but also paved the way for complex life. Beyond Earth, studying weather on other planets offers perspective. Venus, with its thick carbon dioxide atmosphere, hosts surface temperatures hot enough to melt lead, locked under crushing pressure. Winds there whip around the planet at hurricane speeds. Mars, thinner and colder, endures dust storms that engulf the entire globe, dimming sunlight for weeks. Jupiter and Saturn feature storms larger than Earth itself. The Great Red Spot is a hurricane-like vortex that has raged for centuries. These comparisons reveal how delicate Earth's balance is. The mixture of gases, the presence of water, the moderating oceans, all combine to create conditions suitable for life. Change the composition slightly, and the planet could tip toward extremes like Venus or Mars. Weather also intertwines with geology. Erosion from rain, rivers, and glaciers sculpts landscapes. Winds build dunes, carve arches, and transport dust across oceans. Storms batter coastlines, reshaping them year after year. Over geologic timescales, these processes grind mountains to plains and build new features elsewhere. Weather, in essence, is geology in motion. Life itself alters weather too. Forests release moisture and influence rainfall. Grasslands change how sunlight reflects from Earth's surface. Human activity, from farming to industry, now modifies the atmosphere at global scale. Feedback loops connect biology, geology, and meteorology in intricate webs. Looking skyward, the atmosphere connects us to the cosmos. Auroras, shimmering curtains of light near the poles, occur when solar particles strike Earth's magnetic field and energize atmospheric gases. Solar storms, bursts of energy from the sun, can disrupt satellites, radio, and even power grids. These remind us that weather is not confined to Earth. It is part of a larger space weather system that links our planet to its star. In this cosmic context, weather gains new meaning. Each cloud, breeze, or storm reflects not only local conditions, but also planetary and solar dynamics. The warmth of sunlight, the spin of Earth, the pull of the moon on tides, all combine into the rhythms we call weather. Human imagination has long reached for explanations of these rhythms. Before science, people wove stories to explain rain, lightning, and wind. Shamans danced for storms, priests prayed for rain, and cultures tied weather to divine will. These myths reveal humanity's deep dependence on the atmosphere. Only later did instruments and science peel back the mystery. Even today, despite our models and satellites, weather maintains its power to surprise. A sudden storm ruins plans, a hurricane veers unexpectedly, or snow falls where it was least expected. These moments remind us that uncertainty is built into the system. Weather is both predictable and unpredictable, a paradox that defines its fascination. Our future with weather will depend on adaptation. As climates shift, societies will relocate, redesign, and rethink. Coastal cities may build seawalls or move inland. Farmers may grow new crops or adopt advanced irrigation. Energy systems will adapt to extremes of heat and cold. Technology offers tools, but resilience requires planning, cooperation, and humility. Education is part of resilience. Teaching people how weather works builds appreciation and preparedness. Children who learn about the water cycle, clouds and storms grow into adults who respect nature's power and understand how to respond. Knowledge becomes a shield against fear and vulnerability. Art and culture will continue to celebrate weather. Writers will describe storms as metaphors, painters will capture skies, and filmmakers will use rain or sunlight to shape mood. Even in a digital world where screens dominate, people still pause to admire sunsets, snowfalls, or lightning shows. Weather grounds us, reminding us we are part of Earth's living system. The Sleepy Narrator closes with a reflection. Weather is more than background. It is a character in the story of Earth, shaping land, life, and history. It humbles us with storms, nourishes us with rains, challenges us with extremes, and delights us with beauty. To ignore it is to ignore one of the most vital forces in existence. In listening to weather, we listen to Earth itself, breathing, shifting, balancing. From ancient myths to modern satellites, from daily forecasts to climate models, our journey with weather continues. It is a journey of discovery, respect, and coexistence. Weather is not merely a background occurrence. It is a constant force of change, weaving connections between land, water, air, and life. To observe it closely is to see a system alive with balance and imbalance, order and chaos. It is in this tension that weather takes its form, shaping the world around us. One of the most striking qualities of weather is its scale. A single cloud may float above a field, barely noticed, while across an ocean a storm system can stretch hundreds of miles, altering the course of ships and planes. Local weather may shift from sunny to rainy in minutes, yet global patterns unfold over weeks and months, linking faraway regions. These links are revealed in phenomena like teleconnections, large-scale patterns that influence distant weather. El Niño, for instance, originates with warming in the equatorial Pacific but alters rainfall in South America, drought in Australia, and storm tracks across North America. Its counterpart, La Niña, brings opposite effects. Together, these cycles demonstrate how one part of the planet communicates with another through the atmosphere and oceans. Other patterns include the North Atlantic Oscillation, which affects winters in Europe and North America, and the Indian Ocean Dipole, shifting rains between East Africa and Indonesia. By studying these, scientists improve seasonal forecasting, giving farmers, governments, and communities better preparation. Still, prediction remains a challenge. While we understand broad patterns, exact outcomes vary year to year. For example, one El Niño may bring floods, another droughts. The underlying mechanisms are complex, involving not just ocean temperatures but also winds, currents, and feedback loops. The concept of feedbacks is central to weather and climate. Positive feedback amplifies changes, while negative feedback stabilizes them. An example of positive feedback is melting ice. As ice retreats, darker surfaces absorb more sunlight, warming further and melting even more ice. Conversely, negative feedback occurs when warmer oceans cause more clouds, which reflect sunlight and reduce warming. These interactions make the system dynamic, sometimes unpredictable. Clouds themselves remain one of the greatest puzzles in atmospheric science. They form from simple processes, condensation of water vapor on tiny particles, but their behavior in the climate system is highly complex. Some clouds trap heat, warming Earth, while others reflect sunlight, cooling it. The balance depends on altitude, thickness, and particle composition. Accurately representing clouds in climate models remains one of the hardest tasks scientists face. Precipitation, too, is full of intricacy. Rain may seem straightforward, but the path from vapor to droplet is delicate. Turbulence, temperature gradients, and particle collisions determine whether clouds produce drizzle, downpours, or snowflakes. The beauty of a snowflake, with its hexagonal symmetry, reflects molecular geometry and atmospheric conditions during formation. No two are identical, each a frozen record of its journey through the air. Lightning is another mystery that continues to fascinate. Within storm clouds, rising and falling air separates charges, creating electric fields strong enough to pierce the atmosphere. The result is a sudden discharge, lightning, that heats air to tens of thousands of degrees, producing thunder. Despite centuries of study, many details remain uncertain, such as exactly how initial sparks form. What we do know is that lightning shapes chemistry in the atmosphere and poses both hazard and awe. Thunderstorms, hurricanes, and tornadoes all showcase the atmosphere's energy. A thunderstorm may tower miles high, with updrafts lifting air at tremendous speeds. Hurricanes, vast rotating systems, draw their strength from warm oceans, converting heat into powerful winds and rains. Tornadoes, though smaller, concentrate wind into violent funnels, capable of leveling towns in minutes. Each reveals the incredible power stored in air and water. Yet alongside extremes are the gentle patterns of everyday weather. Breezes carry scents of flowers, morning dew sparkles on grass, and clouds drift lazily across blue skies. These quieter moments remind us that weather is not only dramatic but also serene. It nurtures as much as it threatens. Cultural traditions often celebrate this duality. In some places, festivals mark the arrival of rains, while in others rituals thank the sky for sunshine. Farmers still watch skies for signs of changing weather, blending modern forecasts with ancestral wisdom. Proverbs and sayings persist, passed down through generations, reflecting humanity's long dialogue with the atmosphere. Modern society, however, sometimes forgets this dialogue. Technology shields us from weather. Climate-controlled buildings, vehicles, and global supply chains reduce daily dependence on local skies. Yet events like storms, floods, or droughts remind us of our vulnerability. In moments of disruption, the old truth resurfaces. Weather remains a master force, regardless of human progress. Science continues to refine how we interact with it. Remote sensing allows us to observe storms forming across oceans days before arrival. High-resolution models simulate local effects like urban heat islands. Data from billions of smartphones even contribute, as pressure sensors in devices provide additional readings. Every advancement deepens our ability to anticipate and respond. Still, limits remain. Forecasts may improve, but certainty never reaches 100%. This uncertainty must be embraced, not feared. It teaches humility and prepares us for flexibility. The goal is not to predict every raindrop, but to understand risks and respond wisely. As weather research advances, so too does its importance in policy. Governments consider climate resilience when designing infrastructure, from stronger levees to elevated roads. Insurance companies adjust rates based on storm frequency. Public health officials prepare for heat waves or cold snaps. In all these areas, understanding weather is not optional, it is essential. Education plays a vital role in this preparation. When people understand concepts like pressure, humidity, or fronts, they interpret forecasts more effectively. Knowledge transforms warnings from abstract numbers into meaningful actions. A community that knows how weather works becomes stronger and safer. The Sleepy Narrator gently reminds us that weather is both science and story. It is the rhythm of mornings, afternoons, and nights. It is the song of raindrops, the whisper of winds, the crash of thunder. It is a reminder that we live in motion, surrounded by forces larger than ourselves, yet intricately tied to our existence. To step outside and feel the air is to participate in this grand cycle. Every breath we take once passed through clouds, forests, and oceans. Every drop of rain fell once before, perhaps centuries ago, in another land. Weather is continuity, an eternal exchange binding all life on Earth. As we continue our exploration, we carry with us both wonder and responsibility. Wonder, because the sky above holds beauty and mystery beyond measure. Responsibility, because our actions now shape weather and climate for generations to come. By respecting and understanding it, we secure a future where humanity and atmosphere coexist in harmony. Weather, in all its forms, is both ordinary and extraordinary. To study it deeply is to realize that what feels like simple daily changes in air and sky is in fact the interaction of immense planetary systems. Each gust of wind, each passing cloud, each storm is part of a global network where forces of physics and chemistry play out endlessly. At the heart of weather lies energy transfer. The sun's radiation arrives unevenly across Earth's surface, stronger at the equator, weaker at the poles. This imbalance sets the atmosphere in motion as it tries to even things out, transporting heat from warm to cool regions. Winds flow, oceans circulate, and storms swirl as part of this grand balancing act. The Coriolis effect, caused by Earth's rotation, bends these flows, creating trade winds, westerlies, and polar easterlies. Jet streams, powerful rivers of air high in the atmosphere, steer storms and divide climate zones. Ocean currents like the Gulf Stream carry warm waters northward, softening winters in Europe. Together, these movements distribute heat, moisture, and nutrients around the globe. Moisture, in particular, is the lifeblood of weather. Water evaporates from oceans, lakes, and soils, rises into the sky, condenses into clouds, and falls again as rain or snow. This hydrologic cycle links every living being to the atmosphere. Without it, there would be no rivers, crops, or forests. Every sip of water we drink was once part of a cloud, a storm, or a snowpack in some other age. The beauty of this cycle is not only functional but poetic. Clouds drifting overhead are both decoration and promise. Gentle rains nurture life, while storms remind us of nature's raw strength. Snow blankets landscapes in silence, while mists soften horizons. Weather offers not just resources but also wonder. Science, however, sees beyond beauty to the underlying processes. By measuring temperature, humidity, and pressure, meteorologists decipher how air masses form, how they clash, and how fronts develop. A warm front, lifting over cooler air, brings extended rains. A cold front, pushing under warm air, sparks storms and turbulence. These dynamics play out daily, shaping the forecasts we depend on. Advances in numerical weather prediction transformed our ability to foresee these changes. Equations of fluid dynamics and thermodynamics, solved by supercomputers, simulate the atmosphere's behavior. Though imperfect, these models allow forecasts days in advance, saving lives and guiding industries. The challenge lies in data. The more observations we feed into models, the sharper the predictions become. Observation itself is a triumph of human ingenuity. From barometers and thermometers to satellites peering from orbit, we have expanded our vision of the skies. Radar reveals rainfall patterns, Doppler systems track tornadoes, and satellites map hurricanes from space. Instruments aboard planes, balloons, and ships collect crucial measurements, building a global network of knowledge. Yet even with these tools, uncertainty persists. Small errors in data or limitations in computing ripple outward, magnifying in forecasts. This is the essence of chaos in the atmosphere. Still, forecasters refine their craft, blending model outputs with human expertise. A skilled meteorologist interprets not just data, but also context, history, and experience. Weather also reminds us of vulnerability. Despite modern technology, societies remain exposed. Hurricanes devastate coastlines, droughts cripple agriculture, and blizzards paralyze cities. Extreme events test resilience, forcing communities to prepare, adapt, and recover. In many places, local wisdom complements science. Traditional practices passed down through generations offer guidance alongside forecasts. Our relationship with weather is also psychological. People find joy in sunshine, melancholy in rain, and inspiration in storms. Seasonal changes influence moods, health, and behavior. Cultures adapt rituals, celebrations, and daily rhythms to the sky. In this sense, weather is not only physical but emotional, shaping human experience as profoundly as any landscape or culture. The economy, too, is tied to weather. Agriculture depends on rainfall and temperatures. Energy demand spikes in heat waves or cold spells. Transportation slows under snow, fog, or hurricanes. Tourism thrives under sunny skies but falters in storms. Billions of dollars shift with each season, each storm, each unexpected change. For industries, forecasting is not just science, it is survival. As the climate warms, the stakes grow higher. Weather extremes intensify, testing the limits of adaptation. Rising seas compound storm surges, droughts worsen under heat, and wildfires spread faster in dry conditions. The line between natural variability and human-driven change becomes sharper, reminding us of our impact on the system. Yet there is resilience and ingenuity. Renewable energy harnesses sun and wind, directly converting weather into power. Farmers adopt new techniques, guided by forecasts and research. Cities develop green infrastructure, planting trees to cool heat islands or designing drainage for heavy rains. These adaptations reflect humanity's ability to learn and respond. In exploring weather, we also explore identity. The way people talk about skies, storms, or seasons reflects their culture. Desert dwellers may speak of rare rains with reverence, while islanders read clouds to predict winds. Mountain communities know avalanches and blizzards, while coastal peoples live by tides and storms. Language itself carries traces of weather, shaping metaphors and expressions across the world. The Sleepy Narrator reminds us that in every breath of wind, we hear Earth's voice. Weather is a dialogue between sun and ocean, between land and sky, between nature and humankind. Each forecast is a translation of that dialogue, each observation a glimpse into the ongoing story. By learning to read weather, we not only prepare for storms but also learn patience, humility, and awe. We see how small actions ripple outward, how vast systems intertwine, and how fragile yet resilient our world remains. In this awareness lies both safety and wonder. So the next time you feel rain on your face, or watch clouds drifting at sunset, remember, this is not just passing air and water. It is the great system of Earth in motion, carrying history, energy, and life within it. Weather is not just what happens outside, it is part of who we are, shaping us as much as we shape it. Weather is often thought of as fleeting, a passing moment of sunshine, rain, or wind. Yet when examined deeply, it reveals itself as an intricate and unending system, always moving, always reshaping, always reminding us of the vast forces that govern Earth. At the foundation of weather is the constant exchange between energy and matter. The sun fuels nearly all processes, warming air, evaporating water, and driving circulation. Earth, in turn, radiates energy back into space, balancing input with output. When this balance tips, patterns shift, sometimes subtly, sometimes dramatically. Atmospheric circulation is one of the most important results of this imbalance. Warm air rises, cold air sinks, and Earth's rotation bends these motions into vast systems. Trade winds blow steadily across the tropics, while jet streams race at high altitudes, guiding storms. Without these circulations, heat would stagnate at the equator while the poles froze further. Instead, the atmosphere constantly redistributes energy, creating the weather we feel. The water cycle threads through this motion, connecting oceans, rivers, skies, and land. Evaporation turns liquid to vapor, condensation forms clouds, and precipitation delivers water back to the surface. This endless exchange sustains ecosystems and civilizations alike. A single storm may release water that nourishes crops, refills reservoirs, and carves landscapes all at once. Each droplet falling today has cycled countless times through seas, skies, and soils. Weather's role in shaping landscapes is immense. Rain carves valleys, snow builds glaciers, and winds sculpt dunes. Over centuries, these forces transform mountains into plains, rivers into deltas, and coastlines into shifting forms. Geology and meteorology meet here, with atmosphere wearing down rock and redistributing Earth's surface. Equally profound is the connection between weather and life. Plants depend on sunlight, rain, and temperatures. Animals adapt their migrations, breeding, and survival strategies to seasonal cycles. Human societies, too, have always lived in rhythm with the sky. From ancient calendars marking solstices and equinoxes to modern forecasts guiding industries, weather dictates how we live, work, and plan. But weather is not always gentle guidance. It is also force and fury. Hurricanes gather strength over warm seas, turning into engines of destruction. Tornadoes twist through plains, their winds capable of ripping buildings apart. Blizzards bury towns in snow, and heat waves silently claim lives. These extremes are stark reminders of our vulnerability. The psychological effects of weather run just as deep. Sunshine uplifts, gray skies weigh heavily, storms stir both fear and wonder. Cultures have long tied mood and meaning to the sky, from songs of rain and wind to literature steeped in storm imagery. Even modern people, surrounded by technology, pause to marvel at sunsets, to dread thunderstorms, to welcome spring warmth after winter's chill. Technology has not removed us from weather but has reshaped our relationship with it. Satellites watch clouds form over oceans, radar scans rainfall in real time, and computer models extend forecasts further than ever before. These tools save lives by warning of storms, floods, and heat waves. Still, forecasts are never absolute, for the atmosphere remains chaotic, a system where small differences amplify into large uncertainties. This chaos is not weakness but a fundamental truth. Weather is sensitive because it is alive with motion. Scientists accept uncertainty, providing probabilities rather than certainties. A forecast may say there is a 60% chance of rain, not as indecision, but as the best expression of complex outcomes. Learning to interpret and respect these probabilities is part of weather literacy. Education is vital here. Understanding what pressure, fronts, or humidity mean helps people act wisely when forecasts warn of danger. A society informed about weather is safer, stronger, and more resilient. Knowledge becomes a kind of shield, turning raw data into life-saving decisions. Weather's economic importance cannot be overstated. Agriculture relies on timely rains and predictable seasons. Energy grids strain under heat waves or cold snaps. Transportation halts in storms, costing billions. Tourism thrives on sunshine but suffers under clouds. Industries from shipping to construction adjust daily to the sky. Forecasts, therefore, are not just scientific, they are financial and social necessities. Climate change intensifies these concerns. As the atmosphere warms, weather patterns shift. Storms grow stronger, droughts lengthen, and floods increase. The once familiar rhythm of seasons wavers, creating uncertainty. Communities face the dual challenge of reducing emissions while adapting to changes already underway. The future of weather is now a global concern, tied not only to science but to policy, economy, and ethics. Yet weather is not only a source of risk, it is also a source of hope and possibility. Renewable energy captures winds and sunlight, directly transforming weather into power. Farmers use advanced forecasts to reduce waste and improve yields. Architects design buildings that naturally cool or warm with air flow and sunlight. By learning from weather rather than resisting it, humans create sustainable ways forward. Culturally, weather remains a symbol and inspiration. Storms in art represent turmoil. Calm skies symbolize peace. Music imitates rain, thunder, and wind. Films use weather to set mood, from sunny romances to storm-filled dramas. Weather is both metaphor and reality, bridging imagination and experience. For individuals, weather is deeply personal. A child splashing in puddles, an elder recalling harsh winters, a traveler watching clouds from an airplane window, all experience weather in ways tied to memory and emotion. It becomes part of identity, shaping how people remember places and times in their lives. The Sleepy Narrator reminds us gently that to watch the sky is to participate in Earth's great system. Weather is the atmosphere speaking, sometimes softly through breezes, sometimes loudly through storms. It connects continents, feeds rivers, sculpts mountains, and nourishes life. To understand it is not only to know science but also to feel belonging. Every forecast, every observation, is a reminder that we share one planet, one atmosphere. What happens in one place ripples outward, from dust storms crossing oceans to greenhouse gases warming globally. Weather is local in experience yet global in cause and effect. And so, as we listen to the winds and rains, we hear more than momentary changes. We hear the story of Earth itself, its balance, its fragility, its strength. Weather is not apart from us. It is us, interwoven with our history, our future, and our daily breath. Weather, in all its patterns and surprises, is both a reflection of Earth systems and a mirror of human experience. To conclude this exploration is to see not just clouds, winds, or rain, but the deeper connections that bind atmosphere, ocean, land, and life together. At its simplest, weather is energy in motion. Sunlight strikes the earth unevenly, heating air and oceans differently across regions. Warm air rises, cool air sinks, winds flow, and water cycles endlessly from sea to sky. Yet within this simplicity lies complexity. Interactions that create storms, gentle breezes, calm days, and violent tempests. This complexity is why forecasts, though increasingly precise, remain limited. The atmosphere is a chaotic system, sensitive to the smallest disturbances. A shift of pressure here, a ripple of wind there, can alter the path of storms or the fall of rain. Scientists describe this sensitivity as the butterfly effect, and it ensures that while short-term forecasts are strong, long-term certainty is impossible. Instead, probabilities guide our understanding, offering ranges of outcomes rather than guarantees. But this uncertainty should not be seen as failure. Rather, it is a reminder that weather is alive with motion, never fixed, always changing. The very unpredictability that frustrates us also gives weather its character. Without surprise, there would be no wonder in a sudden rainbow, no awe in a storm breaking unexpectedly, no joy in the first snow of the season. The influence of weather stretches across every human endeavor. Agriculture thrives or fails with rainfall and temperature. Trade once depended on predictable winds across oceans. Wars have been won or lost under snow, fog, or storm. Today, energy grids, transportation networks, and economies worldwide hinge on the forecast. A single hurricane can alter markets. A drought can reshape politics. Weather is not just background, it is an actor in history. Yet alongside its power, weather gives beauty and meaning. A sunrise coloring clouds in shades of pink, a cool breeze on a summer evening, the hush of snowfall, all are experiences shared across cultures and centuries. These moments connect us not only to nature but to each other, as people pause to notice the same skies and storms. Cultural expressions of weather are endless. Myths describe gods of thunder, rain, and wind. Songs celebrate sunshine or lament gray skies. Art captures the drama of clouds or the tranquility of clear horizons. Even language itself is shaped by weather, with metaphors of storms for conflict, sunshine for happiness, and seasons for... In the scientific age, our tools reveal weather with new clarity. Satellites track storms across oceans, radar sees rainfall within clouds, and computer models simulate atmospheric flows. These achievements save lives and guide decisions. But even with the most advanced instruments, weather retains its mystery because it is not only a set of equations, it is an experience, lived and felt by every person. As the climate shifts, weather's importance only grows. Warmer oceans feed stronger hurricanes. Heat waves lengthen, wildfires spread, and droughts deepen. Floods strike with greater frequency, and once rare extremes become familiar. These changes remind us that the atmosphere is fragile, responsive to human influence as well as natural forces. The responsibility then falls on us. By reducing greenhouse gases, by planning resilient cities, by protecting forests and oceans, humanity can influence the trajectory of future weather. Though we cannot control storms, we can soften their impact, prepare for their arrival, and lessen the drivers of extremes. In this balance lies the future of our relationship with the sky. Adaptation takes many forms. Farmers adjust planting times or crop varieties. Engineers design infrastructure to withstand floods or heat. Communities build shelters, improve drainage, and share forecasts widely. Technology assists, but resilience also depends on cooperation, and weather affects all people, and so responses must be shared. Education is central to this adaptation. A child who learns the water cycle sees rain not as inconvenience but as necessity. A family who understands forecasts responds quickly to warnings. A society that values meteorology invests in safety and innovation. Knowledge turns vulnerability into strength, fear into readiness. Beyond science and policy, weather offers daily gifts. It is the rhythm of mornings and evenings, the changing backdrop of life. It teaches patience through delays, gratitude through clear skies, resilience through storms. It grounds us in the present, reminding us that no matter how advanced humanity becomes, we remain part of nature, shaped by forces far larger than ourselves. The Sleepy Narrator leaves us with this reflection. Weather is not something outside of us, separate and distant. It is within us, shaping how we live, how we think, how we dream. Every story of humanity is written under skies, carried by winds, touched by rain, or warmed by sun. Weather is the thread connecting us to Earth, to history, and to the cosmos itself. To listen to weather is to listen to Earth breathe. To watch clouds drift is to witness physics and poetry at once. To stand in rain or snow is to be reminded that we are participants. Weather is the atmosphere's language, and in learning it, we learn more about who we are. So, when you next step outside, pause for a moment. Feel the air, look at the sky, listen to the wind. In that moment, you are part of something immense and timeless. Weather is more than forecast, more than data. It is life unfolding, endlessly renewing,